My name is Filip Jančík. I am from Institute of Animal Science in Prague, and I will lead today's section together with my colleague from Mendel University, Docent Hajduk. And today start just same like yesterday, Professor Nussio, which tell us something about oils and fatty acids as additives in silages. Can start.
Thank you very much. Good morning. Oh, please, good morning. Oh, thank you very much. I'm here again. Okay, so today I'm supposed to deliver to you some issues from our research from our group in Brazil. So this picture is part of our group. I'm very proud to be with them all the time. They are helping me in many ways. And this is the group from our lab from forage conservation. Nowadays, it's not only forage. We are doing trials with grain and also co-products conservation. And my main issue will be the essential oil compounds and fatty acids as a strategy for rehydrated grain silages. We are doing a lot of these rehydrated grain silages, mainly right now for beef cattle. Okay, but first of all, I would like to address this invitation to you. This next November, we will have our next edition from our Congress in Brazil from Forage Conservation either. Jambor has been there many times, and some of you may be there too. So likewise, I have done the invitation yesterday to participate in the International Silage Society. You can grab from QR code all the details to participate there. We'll have companies, we'll have people from the university. Most of the people will be from South America, but we'll have international speakers from many, many different countries. So this is the invitation to you. And the next one is the picture from the website and the city of Piracicaba where we are from. So I hope to see some of you over there. If not, we do have the remote linking. So you can either participate by remote linking if you are willing to. Okay, let's move on. So this is pretty much the thesis of one of our former students, Álvaro. Álvaro has been done this during the master and the PhD. And today, I will present to you a sequence of trials which is following the review that you have in the proceedings. So in the proceedings, you have a very comprehensive review about these essential oils and fatty acids that we try to require from the literature most of the information related with the use of those compounds either in ruminant nutrition or in forage conservation. After we have done the review, we selected the best treatments and dosages, and then we started with the second stage of this. So the main question behind of this is, why are we studying this? Well, we have to be creative because all the time we are struggling on the international marketing. This is not new for you, but Brazil is very competitive on the beef in the international market, and most of the time the international marketing is requesting more and more from our industry. So this is one of the strategies, try to find out new additives, and those new additives supposed to be best fitted to the international requirement. Okay, so what is the major background out there? We do have microbial inoculants. We have seen yesterday many beautiful, wonderful trials regarding this. They are already commercial available, and they are feasible, and they will be there forever, better and better, okay? We are almost not not exploring this properly in a worldwide position for the essential oils. We still have an incipient interest on them. The current focus of as feed additives is more for ruminant nutrition, and the crude oils, instead of a molecular approach, is more often released over there. So we have more plant extracts, we have more oils coming from some plants than the molecular isolated by themselves. So pretty much we have a mix of compounds acting at this level by now. And as far as the seed oils is still something that we almost know barely about this. So what do we know about essential oils? I can tell you, most of the time, the deep learning on essential oils as additives for xylene is coming from China. Most recently, most of the basic trials are developed in China. When you, very often you have the microbiome and the metabolomics together to try to understand the pathways which they are acting to. And pretty much I can tell you they can enhance the lactic acid production. In some way, they can also generate the preservation of a protein and a greater dry matter recovery, less losses. And sometimes they can also improve the aerobic stability. So this is the most consistent so far. And we have many, many different compositions on that. When we talk about the corn silage, so we have much less. We will have some compromise of the fermentation when we are using the essential oils. The opportunity for enhanced proteolysis, sometimes it might be interesting because some of the proteolysis in corn silage is regarding the starch availability, mainly when you are driving your thoughts towards the starch degradability in the rumen. And you may have some enhancement on the aerobic stability. Other silage is still very inconsistent results. So now if we shift our thinking to the fatty oils as silage additives, what do we know? There is a scarce information out there, not too many. We do have a lot in the rumen, but we do have a few information as far as the xylene. So we know, for example, the oleic acid can be converted to C19 in a cellular membrane, and there is a survival rate, a higher survival rate of harsh environments, like freezing, low pH, whatsoever. The low degradation of carbon chain in the silo can be one thing that is well stated over there, and the enhancement of aerobic stability is a possibility. So what we have done after we have done the review, you do have available on your proceedings the large review we have proceeded. After the review, we set up 3 steps. The step number 1 we call the screening trial, when we decide about some molecules and the traditional additives. The stage number 2, we have refined the application rates, and we describe the microbial and fermentative modulation. And the stage number 3, we start with animal trials to make sure how often those compounds may change the sorting behavior and the feeding behavior at all. So here you have some very simple explanation about the design. We have the rehydration of mineral water and hand spray in the application of treatments. We use some plastic buckets as lab silos. And this is pretty much our targets. We target close to 40% moisture in the grain. Our previous trials are challenging us that we need more moisture in order to have a better starch degradability. So we cannot afford to have less than 35. That's why, because this was a very precise trial, we could improve the water amount in the system. All all our recent data is shifting our mining in a way to have more moisture there. The fermentation will be better and the starch digestibility either. So this would be the pH and the processing, the degree of processing, and the grain particle size and the surface area of this. So what was the first set of treatments? I'm sorry, to compare the strategies. We started with the 15 strategies. On your left side, we have what I call the traditional ones. So we have a control, we have a sodium benzoate, adding as a 2 grams per kilogram. And then we have the microbial inoculants. In this particular one, we have a formulation coming with L-bacteria, L-plantarum, and acid propionese. We could have any other microbial. The microbial that here is adjusted to have a kind of a reference point. On your right side, we have the first setting of dosages and compounds that were pre-selected from the review in the literature. So we use the carvacrol, cinnamaldehyde, D-limonene, and citral. Why? Just because those were the ones that offer us during the review some potential opportunity. It doesn't mean that some other molecules could be there either. For sure they will. But this one was our decision, okay? Okay, as far as the fatty acids possibilities, we have the same control in your left side. On the right side, you have the decision for the molecules coming from the fatty acids. So we have a lauric acid, stearic acid, oleic, and linoleic acid. And the dosages, again, they were defined based on the meta-analysis on the review. Even though we have recovered from the literature overall 409 papers published with those molecules, but we only have as a final decision for the meta-analysis 28 studies. All the other studies, for some reason, they were not useful at all. Or either because they were only in the rumen, or either because they were not comparing properly the control. There was a lot of suppositions to decide which ones will be in the meta-analysis. So please follow the proceedings. You understand how we decide about this. And we look to the data. This is the very first attempt to understand how they would work. Here is the essential oil compounds, and you have what we call this the trial 1. We open with 30 and 60 days, and then we measure the losses, the pH, and the aerobic stability, and we can have some opportunity to understand a better results for cinnamaldehyde compared with sodium benzoate. So this was pretty much what we could identify in the first step. For the fatty acids, we did the same, and this is first screening offer us a better perspective on the 30 and more in the 60 days as far as the aerobic stability. As you can see, many other compounds would be more effective in the aerobic stability compared with the sodium benzoate. I'm afraid about my time, dear Chairman. I'm okay? Okay, thanks God for that. So this is the stage number 2. This, we already have a setting of a better decision about the dosages. Again, we are not following some commercial products. We are using pure formula of molecules here, because we were intending to isolate the effects. Otherwise, we never know what you're doing as far as the molecule. So for carvacrol, we come from 1 to 3 grams per kilogram. Oleic acid, 0.5 to 2 grams per kilogram. Cinnamaldehyde from 1 to 3 grams per kilogram. And linoleic acid from 0.5 to 2 grams per kilogram. And we have done the number one so-called the trial when we compare 30 and 60 days, and the trial B when we have a time tracking with several times, then we can have a curve for all the treatments. So, and then we use the vacuum sealed the bags for that. So here are some of the outcomes for Carvacrol. In the top graph, you have the trial 1, and you can compare 30 and 60 days. What we observed, the best results were maximized. The optimum was below 1 gram per kilogram. When you consider the gas losses, now you have to move to a decision to more than 3 grams per kilogram, and silage pH is close to 2 grams per kilogram. I will not have time enough to go one by one, but just to let you know that depending on the variable you are considering, the optimal dosages will be different. Is this clear to everybody? So we'll never have an optimum dosages, the same one that can optimize at the same time all the variables. You will have to decide if you are leading more for aerobic stability or in a different way. When you have the aerobic exposure, the dry matter losses were greater at 1 gram per kilogram, and aerobic stability compromised at 1 gram per kilogram, talking about Carvacrol. So uncommon natural fermentation suggests the application rate of 2 grams per kilogram. When we move to the trial B, as I mentioned to you, then now we have the time tracking for these first 30 days to try to understand what is going on with the different dynamics. So again, I will not go one by one, but this is the figure, the way we conducted all the trials. Cinnamaldehyde, using the trial A, dry matter losses optimum with 2 grams per kilogram, gases losses no major benefit with more than 1 gram per kilogram, and the silage pH was a quadratic effect, and the lower pH 1.5 grams per kilogram. When we open up the silos, the dry matter losses were greater at 1 gram, and aerobic stability was compromised at 1 gram per kilogram. So 1.5 gram per kilogram of fresh matter was decided to be the best one for that. And for cinnamaldehyde, as you can see, is more evident across the time the benefits of a larger dosages. The higher dosages were more benefited across the time. Okay, in cinnamaldehyde, we have observed another situation. There was a very clear expansion, we call this swelling, on these vacuum bags with the generation of gases. And the changing on the color pattern of this grain silage, you will be seeing more clear in the next slide. But as you can see in this one here, as we use the 3 grams per kilogram, we also have less zein degradation. So this is a very critical point. In grain silages, we are willing to have some degree of a proteolysis to have a more starch digestibility. However, some of those molecules, they inhibit the proteolysis, which also inhibit the starch degradability. So the bag expansions was pretty much related with the gas production and the proteolysis. So the minor swelling was 1 gram per kilogram, and the absence of swelling of 2 or 3. Okay. So here you can see the difference pattern in color. It's not only the swelling, but also the color is changing, and then very probably we have some antioxidant changing on this. So now we are under this analysis. Right now, our samples are in the lab. We are doing the microbiome, metabolomics, and the identification of some of those antioxidants as remaining in this silage. And the trial B, the same. You can see the difference there. Okay, now we move to the oleic acid. This is the number 3. The dry matter loss is 1 gram per kilogram. Gases loss is a quadratic effect. A minimum loss is at 1.6. And the silage pH, a minor effect of 1 gram per kilogram. As we open the silos, the minor effect with the increasing rates and aerobic stability, no compromise. Our decision was about 1 gram per kilogram. And across the time, as you can see here, oleic was also pretty much not too much different from all the treatments. And finally, we have the linoleic acid. The minor effect was a minimal losses as 0.5 or 0.8. The gaseous loss is 1.1. And the silage pH was inconclusive. And we opened the silo 1.1, the dry matter losses, and 1 gram per kilogram was the uncommon natural fermentation. Okay. So with this, we move for the last step, which is the animal trial. So why we were afraid about the results from the animal trial, based on the basic information from the lab. Because most of the time, those compounds that we mentioned, the essential oil, mainly, they will change the pattern of ingestion behavior from the animals. So for this, we have a group of 28 crossbred Nelore and Angus animals. They were rumen cannula fitted. And so we have a pre-adaptation of 15 days. And then we have the treatment allocation. And then finally we have the metabolic trial. And this is the diet that we were testing the animals. We have about 20% sugarcane bagasse as a raw fiber in the diet. We have 50% of the dry matter as this ingredient as a corn rehydrated grain silage, some a small amount of corn grain, and citrus pulp and protein mineral supplement. So this is stage 3. We rehydrated the silages. We have these 4 treatments: control, carvacrol 2 grams per kilogram, cinnamaldehyde 1.5, and oleic 1 gram per kilogram. And in your left side, you have some of the outputs from the volatile compounds that were produced during the ensiling. As you can see, ethanol in red, but most of the time acetic acid being changed accordingly, and the lactic acid pretty much enhanced by cinnamaldehyde. Okay, this number 3 data, we measure the feed intake, we have the feed sampling, we have the measurement of sorting behavior, the ingestion behavior, the total tract of apparent digestibility, the rumen content, and the ruminal fermentation parameters, and finally the blood samples to analyze the immune system from the animals. This is some of the results coming from the sorting behavior. As you can see here, what is a little bit impressive is cinnamaldehyde is changing completely the sorting behavior as the dosages were increased. When you look to the other data, they are not too much different. So it is interesting because animals were searching for larger particles when we are adding cinnamaldehyde to them. This is really interesting. We're still searching why they are looking for this, and the ruminal data is giving us a clue about this, but not all the information behind. Oleic is more a neutral sorting behavior. As you can see here, the red bars is again showing us a changing coming from cinnamaldehyde for both crude protein and ether extract digestibility into the rumen, which is being reduced. Our ruminal fermentation profile was also changed, and cinnamaldehyde delayed the short-chain fatty acids, mainly acetate production. It was a delay on acetate production, and oleic has a similar responses, although not different from the control. And this will give us the idea that some of the compounds that were working in the silage, they also have been working at the rumen level. So I just want to give you a short break here and a mindset that this will make things very complicated when you are registering products that will be working both in the silage and lately in the rumen. For those of you that are regularly dealing with the registration of products, be prepared, because this will be a challenge, okay? And finally, I just have here very few information about the immune system, because we were dealing with antioxidants, and there were some previous data, mainly from the Chinese literature, regarding the antioxidants in the silage and the consequences in the immune system from the animals. So we have done all these parameters which are listed there, and some changes, but they were not too many. There are slight changes in some of these. I didn't have time enough to list to you all the immune responses, but we have done a lot of exploration, anti-inflammatory effects, and the non-inflammatory effects. Okay, so, Mr. Chairman, I'm coming to the end. This is the final considerations, one by one, to in order to try to make this easier. So, carvacrol, there is a compelling evidence of LAB modulations toward the heterolactic fermentation pattern. We are still unable to control Clostridia. This is a problem. I didn't have enough time to explore this, but some of these compounds, they stimulate Clostridia. So, it is inconsistent as preventing storage losses, more prone to increase them, and unfavorable trade-off between hygienic quality and post-opening aerobic stability. So carvacrol deemed unsafe for this comparison so far. Cinnamaldehyde is capable to modulate LAB towards the heterolactic fermentation pattern, is very consistent on enhancing silage acidification, is controlled the silage environment, inhibiting the late fermentation activity, is desirable and predictable practical outcomes, reduce storage and post-opening aerobic losses, and suggests a range of application between 600 and 1,500 milligrams per kilogram. There is some evidence of antioxidant, and cinnamaldehyde treated the grain silages conferred a strong accent to the TMR and the shifting sorting pattern. So far, cinnamaldehyde was safe for use. Oleic acid is capable for modulation of LAB, is limited fermentation benefits, unable to inhibit Clostridia, inconsistent to prevent storage losses, and enhance the post-open aerobic stability, and suggests the range would be in between 200 and 1,000 milligrams per kilogram, is neutral as a sorting pattern, and improved the immune system. Oleic acid was deemed safe for use for those silages. And finally, the linoleic acid was capable to modulate, is unable to inhibit Clostridia, enhance the post-open aerobic stability. However, it is still inconclusive, and the optimal application rate is too sensitive yet. So, in our perception, we are still behind to recommend this one according to overall data. With this, I will end my presentation, invite you again to join us in our future meeting in Brazil, and thank you very much for your very kind attention.
Thank you for your presentation. I would have one question. Are there some limitation, or can you tell us some suggestion of dry matter content of whole crop silages or grain silage when we can use these additives? Are there some limits, for example, too high dry matter or too low?
Well, we haven't used this with a whole crop silage like corn silage yet. We were dealing with this towards the grain silage because the grain silage industry became very important to us, and the costs of this product in the silo is very high. So if we can limit the dry matter losses, this will be a huge benefit for this industry. We are now moving our recommendations, as I mentioned before, for a little more than 35% moisture, close to 40, as much as possible.
Okay.
If we are below 35 on the grain silage, we may have the chance to have a Clostridia in the silage. We have evidences for that.
Okay.
Okay?
Thank you. Another question? No? So, yeah.
Thank you for this presentation. It was very nice. Is it economically viable to add those compounds to the grain?
We don't know yet. This is, as I mentioned before, this is a kind of a basic trial because we are driving our thoughts towards the molecules to identify the effects of the molecule. So next step would be to understand this in a commercial product. So there is no economic study so far. We hope so. We are betting on this.
Thanks for the presentation, Dr. Nucio. My question is actually regarding what you said about the effect of the cinnamaldehyde on the sorting behavior of the animals. You said you're still not quite sure why they were shifting and preferring selecting longer particles. But then you mentioned that there was a strong smell to the TMR. So is that what you're thinking that's going on over there? Maybe some palatability issues with the cinnamaldehyde?
Well, this is a very good question. Yes, you can feel the smell very strongly. On the dosage that we decide to use, the smell is there and the color is changed too. So somehow animals are searching for more fiber, even though at the ruminal level there was no evidence of acidosis. So usually when animals are searching for more fiber, it's because the rumen is lacking of fiber, or you have a low pH. This was not the case. So maybe we have something else going on over there.
Thank you.
Any question? Okay. So thank you for your presentation.
Thank you again.
Next presentation, we'll have Kay from China, and it's about carbon neutrality and sustainable development in animal husbandry. You can start.
Good morning, ladies and gentlemen. Nice to meet you. So I'm honored to come to here to attend this conference. Thank you very much for Dr. Radico and Mr. Jumbo for the invitation. So today I would like to share some of our research activity related carbon neutrality and sustainable development in livestock husbandry. So we have some project in Southeast Asia and Africa, focusing on animal production, carbon neutrality, and food security. So we had some wonderful memories. Maybe 25 years ago, I attended the 11th International Symposium on Forage Conservation in Brno, Czech Republic. So in that time, I met mining silage expert. So this is radical and maybe Czech scientist. So this is Archibald from Israel. And fortunately, Professor Keith Borson left us forever. So this is DVD. Dr. Keith gave me after his retirement. So now I keep this precious gift very well and try to contribute, commemorate this great contributor to silage. Okay. So let's go to topics. So what is carbon neutrality? It means that carbon neutrality is achieve a balance between carbon emission and absorption in our human activities. So nowadays, many developing countries around the world moving towards to the goal of the carbon neutrality by 2015. So the specific actions use above ground resources like a biomass to replace underground resources such as oil, coal, and natural gas to create a green, low carbon, sustainable society that coexist harmoniously with the nature. Therefore, it's very important to study about agriculture byproduct, animal production, efficiency, and greenhouse gas emission, and agriculture sustainable development. They are all closely related to carbon neutrality. So, as you know, we now at a state global food insecurity. So according to the state, food security and nutrition in the world by FAO 2024. So in the world now, the hunger population is over 333 millions. So it means that 1 in 11 people in the world and 1 in 5 people in Africa will face a hunger. So worldwide, on the demand of food and protein is increased. Therefore, so how to develop agriculture, animal production to improve people's lives? It's very, very important national policy for developing countries. So animal husbandry, it's an industry that raises livestock to obtain animal product for people daily lives. So animal product are a very important source of high quality animal protein, lipid, vitamin, and minerals. So worldwide, in the developing countries, the protein demand can be supplied stably. However, in the developing countries, the supply of protein is insufficient. So from the economic view of the point, the animal husbandry normally connect to other industries will forming a market size about 22 trillion US dollars. Also, the animal product account for 33 of the global protein intake. So there are many programs in animal productions. Yes, the biggest one is global warming. So agriculture sector accounts for 30% of the world total methane emissions. Livestock sector account for 80% of agriculture total methane emissions. So animal husbandry normally can contribute about 15% global greenhouse gases. Their emission amounts are the same as the transportation sector. So the next problem is animal production efficiency is very low. So this table shows the production efficiency of animal product. As grain required to produce 1 kilogram livestock product, the 11 kilogram for beef, 7 for pork, chicken, 4 for chicken, and 3 for eggs. So the protein conversion efficiency from a plant to animal product, there are 40% for chicken, 10% for pig, and 5% for cattle. As you know, the chicken and the pork normally use the concentrated food, easy to compete with the human for food. However, the cow can consume crop byproduct. It's beneficial to green agriculture. They have a new type of the solution bin. Sorry, I forget the English. So normally the straw mulch increase the environmental load, so causing the multiple harms to the atmosphere, soil, water, and the ecosystem. So now in our laboratory, we start to study about the micro plastic how to influence the feed and animal productions. So now we are working for a higher value utilization of the crop straw. So as you know, crop straw production in the world about 5 billion tons every year. So a scientific utilization can return it to resources such as fuel, feed, paper making, and compost. But if discarded, they will become pollution source. Also easy to causing the global warming. So there are some tropical feed resources. As you see, corn stover, sugarcane top, and rice straw. In tropical areas, normally the fresh material can directly used for animal feed. So this is maybe best way to use them. But the dry straw very hard. Sometimes the cattle cannot eat them. So a larger amount of them will burn or throw away like that. So how to use the crop byproduct in tropicals? The fresh material can be made into silage. Silage can store for a long time and can alleviate the food shortage. The drying straw can be made into fermented TMR. TMR fermentation can improve the straw digestibility and animal production efficiency. So for the inferior materials, also we don't throw away, don't burn. We have to use material to make the compost. So the organic fertilizer can reduce the chemical fertilizer and can improve soil health. So this is our project, food security in Mozambique. So we built a bunker silo and to prepare Napier grass silage because the local area lack of the agriculture machine. So sometimes we have to make a silage by handing method. Yes. So also we construct a simple model as grazing in the morning and feeding silage in the afternoon. So this model can maintain dairy cattle for a high milk production and beef cattle for a high daily gain. So this is a TMR. TMR can be prepared with the local available feed resources. Also, we use the simple method to make a TMR. Also, we carry out animal experiments, use local cattle. So the experiment data shows that TMR can be prepared well with the local available feed resources with the rich nutrition and high quality. Also, compared to the traditional feeding method based on grading in the local. So the TMR can improve intake, digestibility, micro production, and profitability. So this is a compost making in Mozambique. We collect feces of the pig, chicken, sheep, cow. Also, we collect the low quality plant material. They cannot make the feed for animals. So we use the ground silo, put the one layer of animal materials and a layer of crop straw, try to keep the aerobic conditions. Also, the local lack of water in the dry season, so we adjust moisture to 70%. After that, we will cover the underground silos. So about the 5 months of the composting, so the compost fermented very well and with the good quality. So the NPK content is about 1.5. So this is a cultivation test. Apply the compost, the grass production can be increased. Also, for the corn production, when you use the compost, can increase the grain pass and the corn store pass. So the grain pass can use for food, and store pass can use for animal feed. This is a carbon neutrality project in Thailand. We set up a monitoring system, methane emission from livestock. So here's a schematic diagram. Consists metabolic unit, sampling unit, and analysis unit. So use this system, we develop green and low carbon animal production technology in Southeast Asia. Also, we successfully develop lactic acid bacteria inoculant in Thailand and prepared fermented TMR with local available feed resources and carry out animal test using local native Thai beef. So the data show that when using the TMR to feed into animal, can increase their body weight, also can reduce methane production. So nowadays we try to construct straw zero waste agriculture ecosystem model through 2 centers. So TMR center can collect straw from a crop farm and then prepare the silage or fermented TMR supplied to animal farm. Compost center also can collect the manure and food residues from the animal farm, and then provide the compost to the crop farm. So this system can effectively use the agriculture byproduct and can reduce green gas emissions. Also, this system can alleviate feed shortage and promote sustainable animal production. So, now we train the agriculture talent for the Africa developing countries. We have some international students study in our level. So last year, we attend the FAO Sustainable Livestock Transformation. So we receive the Innovation and the Transformation Award from FAO. So I went to the Roma, Italy. Also, we actively participate FAO for better activities, try to promote the sustainable agriculture production. So our project carried out in more than 10 countries in tropicals. So I would like to thank all of our colleagues in tropicals. So now I working in Zhengzhou University, China. This is our research team. So if you have opportunity, welcome you. Come to my laboratory. Thank you very much.
Thank you for your presentation. Is some question? No? Yeah.
Thank you for your presentation. It was a big horizontal view, and congratulations to this big effort to make this presentation. I would like to ask you about the importance of methane production of the cow. What do you think about it? And can you suggest techniques, methods, additives? How can we reduce the methane production of the dairy cow? Thank you.
Thank you very much for the question. Because we made the fermented TMR with the high rich nutrition. So when you feed to animal, they are in the ruminant, very efficiency productions. So we compare to the local feeding method based on grading, because that material with the high lignin and fiber, so easy to make the more methane production in the rumen.
And if we have already TMR or PMR in Europe, if we have already TMR or if we have already PMR, there are additional additives or technology to reduce the methane. Can you tell me something about it? You have a horizontal view now.
Yeah, I am not sure. So because fermented TMR within a high amount of the lactic acid, so in the rumen also they can inhibit microbe in the rumen, also can can compete with this one. What's it called? The H2. So yeah. So that means just can reduce the methane productions. Okay.
Thank you.
Yeah.
There is next question.
Just short question to this topic. Did you also calculate how much emissions are when you produce these additives? Because there's also some process and it's also cost energy and yeah. And also second part, because sometimes I don't like to compare with the cow. Cows is eating something what is nature. It's finally cycles. Car is something what you take out of the earth, what was close, and you put it in and it stay here. Cows is cycle. So 2 questions.
Yeah, your answer more professional.
Okay. Yeah. Do you have question?
Yeah, it's actually more of a question on those lines, right? What are we still doing wrong as an industry that we still keep saying this, okay, the animals, yeah, of course, they produce methane. We know that the methane has the potential of global warming that's greater than CO2, but that's the key point, right? Cows eat grass that's actually taken up, so it's part of the biogenic cycle of carbon. So what are we still doing wrong as an industry that we still keep saying that and not really bringing that truth out to public? And what can we do different?
Sorry, I don't understand well. Maybe after
Okay.
we discuss, yes.
Good.
Thank you very
Okay.
much.
So thank you for your presentation. So, and the last presentation of this first part today is about drones, and Sonia Mala tell us something about that. So you can start.
Hello, I'm Sonia Mala, and I'm here to introduce you the thing, the right moment for silage harvest and methods and decision frameworks. Yes, now it's some part of drone, and it's a little bit technique. It's my field. So how to be fine for agriculture. So how you can see, drone cannot be so large anymore, and you can take it in the backpack. And flying is not so hard how many of you think. This picture is not randomly selected. I have one story. If you can see, there is not a perfect field. I was with agronomist, I was staying near the crop, and he said how everything is perfect. Then he take a look at this remote control, and sorry that a word. Oh shit. So take a look how it be fine for agriculture. Take this. Okay, it's working now. So this is a nightmare of the harvest is nightmare of every agronomist. He can see where to start, which region, a lot of fields, more. Very often it's more than 1,000 crops, 1,000 hectares of maize, and probably there is one unpredictable weather. By the way, there is a lot of techniques company, and they try to teach them what NDVI means, and it's just a number. So, and when he take a laboratory, it should be precise, but mostly they have take lab analysis every week, but sometimes it happens the dry matter is lower, but it should be bigger. So at this process of decision usually happen then from the fresh maize is the right field. So this is where the world where the agronomist is in the contact of dairy farm. He bring matter to bunker, but livestock specialists feed it. But usually on each farm, it's a different budget. Something happened in agronomist on the field, but they doesn't track what's happened on the dairy farm. So a lot of farms have not good knowledge about where the prices is. So decision of agronomist, I'm sorry that it's in a Czech, but it's our material for Czech farmers. And it's bunker, 1 year and 2nd year. And decision of agronomists is that conservation is too expensive. So they tried without conservation. And they ask us where 5 tons of material disappear. So, little bit economic. There is a really simple model. I cannot find any economist scientific word how it's go from the field to milk. Usually it's not connected. So just, everybody that imprecise harvest timing mean loss of dry matter and feed quality and reduced profitability. This know everybody, but how much doesn't know. So if you have a well-managed silages, the loss is about 5%. But with a full timing, it's 20%. And occasionally, it might happen that losses is 30% of the matter. So what it means, for example, for small biogas plant, lost 20%, but they have to buy 3,000 tons of silage. Prices is different for each market, but this is for a Czech market. And probably if we calculate it to gas production, if they just don't solve it, and he didn't produce biogas enough, the losses will most larger. So now, agronomists care only about this small point. And they make a decision for whole farm for a year. So optimal harvest time, if you focusing on the yield of the field. So with a poor timing and dry matter losses, you can lose 32,000 euros per year for a small farm. If you have the right silages, you lose feed efficiency, and you can lose around 150,000 euros per year. Okay, quality of food is not good, so there is illnesses. Dairies which are not produce milk for whole weeks. So there is the other losses. And okay, and at the end, if you have a good feed and health cow, the production of milk will grow. So probably at the end, if you can take a close, if you take care about budget of farm as a whole, you will be plus around 400,000 euros per year. And this is, I cannot find any scientific field how it's going together. All schools are only agronomists or livestock, no together. So, and what is, sorry, there is a bad quality, and there is one of the problem. This is a real field with their heterogeneity. There is a road, and agronomists go usually every morning here this way. He called us that it's time to harvest, so measure dry matter if it's okay. I need a quiet place for a drone, so I find this place. And I called him, hey, why you called us? You have a lot of weeks to waiting. And he said, no, it's really near. So after a drone saw that, so he saw that this is quite different maize crop. And what is decision? He usually have to harvest it as a one whole. They don't want to select it like one half of field and the second field. So there is a problematic spots where anaerobic situation might be worse. So just other problems, okay, we get a sample. And we know the neighborhood here. But sometimes happen that it's again like another spot there. So how to deal with that? And this is the reason, okay, one week you take a sample here, and one day you take a sample here. And now you have problematic. So what methods we know how to predict harvest time? We have satellite, drones, on-board need sensor, laboratory analysis. And all these data should lead to real-time decision and data-driven performance. But there is so many data. and we have to find some sense for them and translate it to the simple task for farmers. They couldn't think about, okay, what the satellite and DVI means, what that means. They should know it's harvesting, it's approximately at that day, and probably you need a list of fields sorted by a time. So, how I said the data is too much, and usually it takes 72 hours to take one simple number from whole pixels of images by drone. So now, how you know satellite is oriented, but you cannot care about data. It's just flying around our head, and sometimes we get data, sometimes we not. Drones, now it's really simple to take it with us, and in 60 minutes have a view of how the field looks like. But it's only feeling like from a remote control, you know, you good or bad. Some farmers just take a harvester and just go around and use nears on board to harvest small part of the field and make a decision. Okay, so sometimes they miss the spot. And laboratory analysis is precise, but it takes a time. So there is some disadvantages and advantages of nears on board. One of the best advantages, you scan whole green matter from the wheel. Okay, it's not precise, but you know with some reliability that it's good or no. But other way, after you know it, you cannot harvest it again. It's a one-time process. So when you have a harvester, the one big opportunity advantage is that it homogenizes the matter. It's go to the one big place, and there is mix it and mix it and mix it, and somewhere it go out to the car. But which GPS position it is, where it was grown. If you take a look deeply on this data from QGIS, it's very simple. It's a shapefile. You can open it in a program QGIS. You can see that dry moisture changes very a little bit. It's not like in the real world that you have a green matter and few meters later you have a dry matter. You cannot see it here where exactly had happened. And if you see from the map from New Holland, you can know how the harvester goes. North spot. If there is a spot, there was a spot, but there is a little bit higher. Sometimes I call with the farmers and say, okay, what's your dry matter from the field? And mostly answer is 32, and from 32 to 38. And it's repeatedly from a whole field which I care. So it's same. And they are asking, yeah, okay, we are good. It was livestock specialist asked me, yes, it's okay, we have 32 to 38. And after 6 months, it's opened. And now it's terrible, it's mold, and so on. And they have to buy other, I'm sorry, for Czech, please, vyvazovače. Binder. Okay, there is data for this drone. So you can see there is wet spot and dry spot. Diametrically different. We colored it from the light green to the red. At the end, the diameter was 43. When we choose only green matter, not whole field, because it was damages, we get diameter 42. But harvester, 40.5. I think that drones is pretty near. And laboratory analysis was somewhere in the middle of them. So take a look at satellite. Free satellite Copernicus. Everybody can use it. You have free data. Just in a few minutes you can get an account. And if you have a boundary of the field, you can get the other data. It's a multispectral sensor, but only simple wavelet. It's not like a NIRS, like in the interval, but there is only 10 bands, and they are divided. So you cannot care. You have data. You have historic data. I think every field now there is information to 20 years of history. So you can check it. But the resolution is 10 meters per 10 meters, 1 pixel. So you have only one value, but if you think deeply, harvester has 10 meters, which they mix it. So it could be similar. But disadvantages is, I'll take this one. It was season 2025, and I was very lucky if I have in a month one value, because it was really cloudy. But yields, it was growth. Every agronomist was happy. So there is, as you see, there is boundary of the field. You can see a spot, and there is history 1 year back. So April, mice is growing. Now is July, August, and now it's start drying. And there was harvest. The very good numbers is here, the range. If not just one mean value, but it's a range. How wider it is, you have more bigger problem. And now take a look at the drone. It's same band as a satellite. If you want to take a look, red, green, near, red edge. But resolution is 100 points per meter. So it's much better than satellite. So you can see where white animals going, where is raining, where is wet spot, etc. I forgot. I can find myself in the field. But there is limitation, like on a human work, you have to go to the field. You have to make a decision that you want to measure that. You cannot have historical data, but you know, right now, satellite is cloudy, I haven't got data, I can go directly to the field. But there is airports, there is protected areas, etc. But it's, but still there is a lot of time where farmers cannot solve that. And even you solve it, it's usually person to person, and you make an agreement very easily. So if airport knows about you and you let an email, today I will go there, usually it's very quick to get acceptation. Okay, maybe they said not today, tomorrow, but dealing is possible. And what about prediction? Now we have data from satellite, from drones, and we have imagination of the field, where is wet spot, where is dry spot. So we can translate it, and we can see, and I measure it several times, and it's mostly fit, that if I make this prediction, and I go there 1 week later, it fit. So how it's going? We have a wet field in September, and okay, we cannot go. But maybe somewhere in 5 days, now optimal parts is growing to 50%. Dry matter is 30%. So harvesting started. But still, there is a lot of portion of field, 20%, where if you go through, you stop harvest. But we can't wait. So in this, you can prepare in 3 days, go to the field. So, and it's going similar. I can calculate it for field. And our goal at the end of this is to predict milk production. What is the bad? What is good? From a satellite, from a drones. So now we are dry metals. It's mostly fixed like a near sensors. We can starch and crude protein. It's fit, but there is more range. It's not so straightly curve. And little bit say about 2 pictures on the first slide. It wasn't in time, it was on the same field. And cannot know if these data are applicable if we get samples here. And after that is change. So one for a hybrid selection, for a dry location. How you can see, there is no different anymore. It seems similar, but on the dry spot, only one hybrid is green. So this is a clue how to deal with heterogeneous field. Just select hybrids, the right one. The other case, hydrogel application and crop development. We try to use, we expected that it will look similar. When you have hydrogel, you will be more green maize. But unfortunately, it was a mistake, because everything was same. From a picture, you cannot see a different, no row, just one continuous crop. So I was really disappointed from the Earth observation. But at the end, if I get the data, without hydrogel, optimal area of that field was much lower than with hydrogel. So it was not visible, but we have wider window with hydrogel to harvest. So when we have a lot of fields, we cannot choose which one we will harvest, but we can harvest it in the same stage of maternity, even it's 1 week. So I cannot read this, it's in the proceeding, but if here we was disappointed with lab analysis because it was green part and it doesn't fix with field. And now in hydrogel we have 3 data set which are not compatible. Huawei say 32, lab analysis, I cannot recall how much it was for a lab analysis. I think it was about 34 or something like this, because there was huge portion of corn. And the harvest lab, it was about 40 dry matters. But it was compared like separated data set. So now we're introducing a new project created by the spin-off of Nutrivet, Agratio. And we try to collect data from satellite, lab analysis, with AI, army of ints. No, it was a joke. Artificial intelligence to bring all your data, transfer to one simple view to make a right decision in time. How it looks like? This drone has an application made by me right now, and we can calculate like a harvest lab during the fly. So in 60 minutes, you have dry matter of whole field. it's not precise. They have a limitation because we made calibration here in South Moravia. So we need to, I guess that if we add other location, we have problems with that, but it's calibrated. It might be calibrated. We know that in VVS, in the mountains, it doesn't fit correctly, but we are working on that. But if you have just guess of drone in within 60 minutes, but then you can take a samples like usual and get it to laboratory. And if you have right GPS position, you can calibrate it, same data, and second day you have a precise guess. And now we connected cloud for this drone, and this view can see everybody, anyone on the world at the same time. So you can be in your office and your colleague might be flying on the fly and you will data in real time. So future is connected for our years, and probably there is no question if it's possible. Definitely it is possible, just we have to we have to know how to use that technology. Thank you for your attention. Do you have any question?
So, thank you. I will have one question. You told that onboard near isn't really comparable with drone data. You tested it only with one onboard near or with more producer?
We tested it with New Holland and Harvest Lab. With Harvest Lab we have a problem because a lot of drivers switch off, collecting to the cloud. I don't know why, but it's happened very often. And then its data are the same, 32 to 38. With Dynamica Generale, we have more better experience because you have really GPS position where the calibration samples was taken. So it's comparable. And we have several fields where when it's harvesting, by nears on board. At the same time, I'm flying around it, and then we take a lab in the one day and bring it to lab samples and bring it to our laboratory and analyze it. So I think that is pretty there is no doubt about timing.
Yeah. Okay, have you?
Thank you, Sonja, for this very good presentation. My question to you is the use of the drone for spot sampling for references. Have you experience in that? If you have a better finding, you showed us the problems with spots in the field. And is in your opinion, the drone very helpful to find different spots to reference the drone for or calibrate the drone for better results of dry matter prediction?
I'm not sure, what do you mean, for samples? For sampling? Okay, I love technology, so I looking for different, okay, in mobile you have a GPS, but the resolution is terrible. I haven't no better way than go with drone around above my head and make a picture of me where the samples was taken. And sometimes it's quite problematic to find and identify the exactly 5 plants because the picture is quite bigger. But this is a lot of work, I know it, but it's the best way how to calibrate it drone because you know exactly 5 plants which you take it. Did I answer it?
Some questions still? Yeah.
Thank you, Sonia, for this very informative presentation. It was absolutely new. It's not my area, so maybe my question will be very naive. So, do you have international license? Is it possible to use the drone in other countries? And what do you think about the accuracy of your calibration? What was done here in Czech Republic?
Okay, the technology potential is global. I can send you, if you have this drone, I can send you software which I prepared. The cloud is accessible for all the world. And satellite from Copernicus is no limitation all the world. So potential, it may be globally. But there is a lot of work for calibration. We met it here in Czech Republic that region is different. So we need local cooperation company which will collect data and prepare a data set for our.
So if we would like to use it, for example, in Hungary, we have to refine your calibration, it means. But your personal assistance, so it's not needed your personal assistance because we can buy the drone and we can use the application, so we can make the estimation for ourselves.
Yeah.
But
this cloud should be open. We have own calibration curves, but if any one of you want local based on your laboratory, because it's nonsense to send everything from USA to Pohořelice in one day. So we are trying to prepare community.
Thank you for a great presentation. I would like to ask you how many spots per hectare you use for calibration, or how do you do it? And second questions would be, I don't know, I know it's in German, RTK, you know, this is really position that you can have, because we don't use just handy, we have it connected with this RTK. How it's called in English? Okay, we will speak afterwards. But first question, how many spots?
How many spots? When you have a precision agriculture for a yield, usually there is 3 or 5 classes to get a variable seeding, variable fertilization. So usually the field is divided into 3 or 5 classes. So I guess that 3 or 5 samples from a different area based on different production classes should be enough.
And how large is that area? How many hectares?
In Czech Republic, the maximum size is 30 hectares. 3 or 5. Not this year, but next year we hope that we can give you advice where the samples should be taken.
Sonia, very nice presentation. Congratulations. It's very inspiring. This is just a curiosity. Have you ever tried to measure the chopped particles when the wagon is dumping this into the silo? The forage is already harvested and now is in the silo being packed.
We tried it, but usually from somewhere here. Because you have a lot of fields layered in the silo, so if you come there 3 months later, nobody knows where it is. It's a big problem. But some small farmers with a few fields said, okay, your drone is broken, just don't worry, it's okay. And in the January or February, I guess the same number from the silage samples.
Okay, thank you.
Congratulations, and this is very promising. I want to say that back at home we're still chopping, some plants and then taking multiple samples, so that's very good. My question is if you have thought about using that to maybe try to predict disease, for example, any sort of fungi disease, and try to make a local application instead of a whole field application. Have you thought about that? Maybe this is more agronomic, but I think that there might be some applications for that as well.
I was thinking about that, but for me I first would like to predict dorimeters, have a cloud where we can work with RGB data, with laboratory analysis based on GPS, based on nearest on-board data, satellite data, and then we can combine it and start playing with machine learning based on diseases, based on sorry, for insurance. Because it's really risky discussion when something happened like a big storm, etc.
I see next question. I think now we should have a coffee break. Can I let this discussion to coffee break? Yeah. Okay, because we will start next section at 11:20. Yeah, it's 11:20. So thank you, and now is coffee break. And can I? Yeah.
We will continue with the next section. We have some small delay. And okay, perfect. Great. So I would like to introduce myself. My name is Stanislav Hejduk, as Filip already said, and I'm working at the Mendel University in Brno, Department of Animal Nutrition and Forage Production. So I'm working at the part of forage production, and Dominik Vlk is my PhD student who is co-author of this presentation with me. This topic, which I will present here, is a little bit non-traditional, especially for probably this kind of conference. But I think that, especially in Czech Republic and some other countries, which are a little bit more aimed on the grass seed production, it can be important source of forage for cattle or some other ruminants. Czech Republic is quite important producer of grass seeds, and in this picture you can see it's a quite untraditional way of farming when this is the two-stage harvest of, in this case, Italian ryegrass. So you can see the swords of the grass after the cutting, and now you can see the picking and threshing of the biomass with the seeds and straw, and you can see the green background. What is the regrowth of the grasses, which are perennial, so they can continue the growth after the harvest. What is completely different situation compared to annual cereals. Okay, a little bit about the introduction. So grass seed production is quite profitable agricultural sector if you are able get good yields of the seed. And Czech Republic and some other countries, the #1 state in Europe is Denmark, with much higher acreage. But it produces quite high added value compared to cereals, which are also exported from the Czech Republic. So I think for the state economy, it's a little bit more valuable than just export the grains of cereals. The area of grass seed fluctuated between the years, so you can see the record in Czech Republic was almost 20 years ago when we had at about 20,000 hectares. Unfortunately now the areas are much lower, so we have just about 7,000 hectares of grass seed production in Czech Republic now. But as I said, it's fluctuating according to the prices of the, not just the grass seed, but also some other crops as cereals or seed rape. Grass straw can be used especially for the ruminants with a little bit lower productivity, and very popular it's for the beef cattle or beef cows, especially during the winter time. And during the last 35 years in Czech Republic, the proportion of beef cows increased from 0.1% in 1990 to almost 40% in the last year. So you can see that the importance of the beef cattle increased rapidly, and this type of cattle compared to dairy cows has quite low need nutrients during the winter, so this bulk forage is quite useful for these farmers. We also increased the number of horses, especially the hobby horses. Now there is about 100,010 heads of horses in Czech Republic, and these horse keepers are often without own hay sources, so they also appreciated the sources of the grass straw for feeding of horses. Some other reason for increasing interest about the feeding of grass straw is the drought, because especially in these 3 years I mentioned here, 2015, 18 and 17, there were very high prices of hay in the whole Europe. Sometimes the prices of hay were higher than the concentrates, and most grass straw in these years were fed because there were high scarcity of hay. Yeah? So it's also important to have these sources during these dry years. And for the growers of grass seed, it's important to have some farmers who are interested about feeding of grass straw because it can increase the profitability of seed growers. Otherwise, they just mulch or crushed the straw of grasses for recycling of nutrients, but they have no income from this straw if it's recycled. In this picture, you can see a famous man, Mr. Machach, who was very important man in the research of grass seed production in Czech Republic. Now he's in pension already. And you can see the stand of Timothy, what is one of the important grasses in the Czech Republic for seed multiplication in East Bohemia during some field day. Interesting situation is in Oregon. Oregon in America on the Pacific coast is the most important producer of grass seed in the world. About 50% of the grass seed in the northern hemisphere is produced in this state. And the reason is that there are specific climate that during the growing seasons from October and winter, from October to May, there is a lot of precipitation, plenty of rain, and during the ripening of the grass seeds, there is stop rain, so they can harvest the grasses without any risk of the rain or adverse weather. And in this region, it was quite common practice to burn the straw because in this area there is no cattle, no animals, so the farmers don't need the straw for feeding of animals. And the burning of the straw was very useful or beneficial management because it increased the seed yield of the grasses, especially the perennial grasses as Kentucky bluegrass or red fescue. It eliminated all pathogens, fungi, eliminated thatch, so the regrowth was much faster. It mineralized the nutrients, especially the potassium and phosphorus, accessed light to the grass crown, so it improved the tillering and improved significantly the seed yield in the next year. So it was very popular among farmers. But there were some troubles, especially the people in the cities nearby these big fields complained that the smoke make the trouble for the breathing, make the worse air pollution, and especially the last case was that it caused big traffic problem because during the burning of the straw nearby the highway there was the big accident and a couple of cars crashed and there were a couple of deaths during this accident. And since that time the government in Oregon strictly prohibited the grass burning or the straw burning, and since that time there started export of straw because they needed to collect it, and they started to export the straw to Japan and East Asia because there is the lack of forage. So it's interesting story, and now most of the farmers export the straw from their fields to these regions. This is a picture from Czech Republic, from one cooperative farm where I was working in past, and you can see that quite common practice of the farmers is the crushing of the straw immediately after the harvest by the combine harvester before, without using it for the feeding of animals. I think it's the wasting of nutrients because there are some crude proteins. Of course, there is the digestible fiber which can be used for feeding of animals, but because the number of cattle decreased by 50% in the Czech Republic in the last 30 years, there is not so high need, also big need for the forage as in past. So unfortunately, plenty of the grass fields has this system of management with straw. When we speak about the yields, how much of the straw can we harvest from 1 hectare. It depends on the grass species. In Czech Republic, we multiplied about 15 grass species, so there are big differences in the yield. Some grasses are also bred for the turf grass use, so they are usually shorter, and the grass straw production is lower compared to forage varieties of grasses. So you can see that some species like Timothy can produce up to 12 tons of dry matter per hectare, while some small grasses like Kentucky bluegrass or red fescue produce just about 5 tons per hectare. But when we compare it with average hay yield from perennial grasslands, you can see that the potential yield of the straw is much higher, usually twice or sometimes 4 times higher than from perennial meadows. Yeah? So you can see that the production potential is quite big. Here just is one example of the harvest from our research station in Vatín in the Bohemian Moravian highland between Brno and Prague. So you can see we harvested it with this small threshing machine, and we evaluated some treatments, in this case with ryegrasses. We compared the standard tillage and no-till system. So you can see we evaluated the seed yield, which was quite high, and we also evaluated the straw yield in the dry stand, but also we evaluated the dry matter content. So you can see that there is quite high moisture content in the straw immediately after harvest, so it's necessary to dry it before it can be baled. So from the point of view of forage quality, you can see that the straw from grasses is comparable to late harvested meadow hay, but what is very important, it's always better than cereal straw. Cereal straw is quite frequently used for dairy cows and also for some other ruminants, and I have to say that grass straw should be preferred in the use than the cereal straw. There are also significant differences between the grass species compared to when we compare the straw quality. Not just the yield, but also the quality differs. You can see that the grass straw offer the material rich in fiber. The NDF content is between 64 to 80%, and it's quite low in crude protein, but the range is quite high, as you can see, from 3% in some cases to 12% in the species which are more rich in the leaves. There is quite low proportion of minerals, just 2 to 7%, and the main mineral is potassium, which is important for the grasses. And when we can see comparison between the perennial grasses, in this case perennial ryegrass, meadow fescue, and cereals, oats, and summer barley, it's from the tables of Professor Zeman, 30 years old. So you can see that the fiber content is quite similar between the perennial grasses and the cereals. Crude protein is a little bit higher in the straw of perennial grasses. Digestibility is a little bit higher with the perennial grasses, and also net energy of lactation is a little bit higher. So that's the reason why we should prefer the grass straw before the cereal straw. In this table you can see the results from our trials in Vatín, which are 9 years old when we had this trial. And again, you can see some grasses we tested. So you can see that the crude protein is, in some cases, for example, in this table, Kentucky bluegrass or perennial ryegrass, on the same level as a hay from organic farms. Sometimes they have the same level of crude protein in the hay. NDF is much higher. And ADF, which is more important, is also on the level of the low quality hay, and ash content is, as I mentioned before. So you can see that the protein and energy is quite low in this material, but it provides a bulk and effective fiber for horses and low productive ruminants, and it's also important for the health of the ruminants in some cases. So now you can see NDF content in some grasses. They are the samples from Rožnov research station, and I just apologize for the name of the grasses in Czech, but you can have the names in English, not in Latin, in the heads. So you can see again that the NDF content varies between 65 to 80%. So there are big differences, and it's linked with the leaf proportion. So if you have high leaf proportion, as for example meadow foxtail, there is much better quality compared to stemmy grasses like red fescue or Italian ryegrass or Timothy. And in this case, you can see crude protein content. Again, you can see big differences from 3% to 12%, and it's linked again with the leaf proportion, but also fertilizing with nitrogen can also improve or increase crude protein content. Once we made by mistake twice as high nitrogen fertilizing than we should, and in this case we have also very high proportion of crude protein, but it's not very economically effective to increase the crude protein by high fertilizing. And in this case you can see the picture of the meadow foxtail grass, which is quite common in Czech Republic, especially in the more moist soils, and you can see this grass reach the best quality of the straw with the highest crude protein content, and the reason is that there is very high proportion of the leaves and sterile tillers, which has also higher quality. On the other hand, here you can see the annual ryegrass, which is quite stemmy grass, and in this grass we get very low proportion of crude protein, and also the NDF content is much higher compared to previous grass. In this case, you can see the reviewed nutritional value of just perennial ryegrass straw. Perennial ryegrass is the grass species which is most commonly multiplied in the world, so it's the most frequently multiplied grass from the south hemisphere to the north. And you can see usually the sources from Oregon, but also from some other countries, and you can see the results are quite similar, as we could see before. When we spoke about the minerals, you can see the most important mineral is the potassium. And there is a problem in Oregon that when farmers were used to burn the straw, all the potassium stay in the film, and now when they export it after 10, 20 years, they can see they have very low status of potassium in the soil, and they can start fertilize with the potassium what they didn't do before. Okay, and this is the last table, again from Oregon. You can see it's quite old study, but the studies about the quality of the grass straw are quite limiting. So that was one of the reasons why we started to do it in our country, because most of the sources came from Oregon or New Zealand, and in Europe there are very small data set about this quality of different grasses. So some results are comparable, but some are a little bit different. In this case, you can see the situation when you harvest the straw and you just windrow it before the carting, so it looks very similarly like the cereal straw. And concerning conclusion, so you can see the grass straw has higher nutritional value compared to cereal straw, so we should prefer this grass straw. Second, it can improve the profitability of grass seed producers, what is also important for some farmers in Czech Republic. Also, it can be quite important source of forage in the dry years when the hay is not accessible and the prices are very high. And the last one, it can be suitable forage for low productive ruminants, especially beef cattle, and it provides essential bulk and fiber, what is sometimes also some big trouble to buy it for affordable prices in dry years. And the last picture shows the harvest of the straw from the grassy trials at our resource stations, and I'd like to thank our technicians at the resource station for the technical assistance. So that's all. Thank you for listening.
Have you any question?
Thank you very much, Stanislav, for this presentation. Can you tell me how much are the costs for grass straw in comparison to wheat straw, for example? And can you explain us the importance of supplementation of wheat straw or barley straw, for example, to dairy farms? Yeah? Is it an advantage to use grass straw and not barley straw or wheat straw in dairy farms?
Okay. Okay, Reinhard. So I think it's a little bit different situation in Czech Republic compared to Gumpenstein, because you receive probably better quality of the forage from the perennial grasslands. In our cases, farmers in Czech Republic are mostly focused on the production from the arable land. So the grasslands is the second crop in the importance. So the quality is it's much lower compared to Austrian situation. And when I mentioned the feeding of the cereal straw from the barley or oats, it's quite frequently recommended by advisors in the cattle industry that they need to increase the crude fiber for the rumination and produce more saliva, because especially if you have the diets with a high proportion of the corn silage, there is sometimes lack of this fiber. So most of the advisors use the cereal straw because they can find easily the tables and all the parameters are easily written there. But there are not tables for this grass straw, so that's the reason why they are not aware about this opportunity to use these advantages of the grass straw, because you can get with the same intake more nutrients intake, so you can reduce the concentrate level. Yeah? But unfortunately, the advisor in Czech Republic don't know about these advantages, and they still recommend just the cereal straw. That's the reason.
I would like to ask you, how many hectares for seed production of grasses in Czech Republic?
Yeah, it was mentioned in the first slide. So it's now at about 7.5 thousand hectares, but in past it was 20,000 hectares. Yes? So yeah. It fluctuates. Yeah. But in Denmark, which is a smaller state than Czech Republic, they have 80,000. Yeah? So it's the number one in Europe.
Thank you.
And which price of this material can be expected?
Okay, so it was also part of the question of Reinhard. So as I mentioned, as the farmers usually just mulch the straw or crush it and leave it on the field before the plowing down. So it costs them nothing, but as you could see, after the harvest, the dry matter content is just about 50%, so it's necessary to leave it dry, maybe you can turn it, so it can increase the cost, which is linked with the harvesting, but all the other costs are the same, like for cereal straw, so it can be the same cost for grasses and for the cereal straw.
Thank you very much. I would like to know if you have any experience on the water holding capacity in comparison to wheat straw. For example, if you use it as bedding material in comparison to straw, or also if you feed it to the animals, you usually want a mat in the rumen that is very effective. But how about this material? Is it also effective to build this mat in the rumen?
Okay. Concerning the second part of the question, I didn't test it, so I can't say any exact data about this mat on the rumen, but I expect that it can have the same behavior as the cereal straw, yeah? So it shouldn't be much big differences. But concerning the first part of the question, I have to say that if you use this grass straw as a bedding material, what some farmers do, the cereal straw is much better when we compare the amount of the water which can be fixed on the straw. The cereals are better than grasses, yeah? So it's not so suitable for bedding, but it's much more suitable for feeding.
Yes, you have.
Hello, good morning. Já mám dotaz ohledně trochu jiného tématu, nicméně ohledně silážování řepky. Nemáte někdo v sále zkušenost se silážováním řepky?
Myslíš jako zeleného krmení, jo? Okay, já odpovím teda v angličtině. Concerning the silage of the oilseed rape, because it's brassicas, it's part of my lectures for students. I always say that the brassicas has very low dry matter content, just about 10%. So it's very difficult to wield it to the dry matter content above 30%, which is the safe to prevent the leaching of some fluid material from the silage. And I think that the wilting of oilseed rape is very difficult. So I wouldn't recommend it, at least as a monostand. Maybe if you use it as a mixture with some grasses or some cereals, it could be used, but I wouldn't recommend it anyway because of the very high water content. But maybe some of the audience or from the audience have some more experiences with silage making from oilseed rape. But it's not common at least in Czech Republic. Well, probably nowhere.
So if it's everything, so thank you for your presentation.
Okay, fine. Thank you for the questions. And I will continue with chairing of the conference. And I'd like to invite the next speaker, who is Mr. Aro, if I say it good. And the next lecture will be aimed on the impact of the oxygen barrier film and the preservation of the corn silage. So the stage is yours and microphone also.
Okay, good morning, everyone. My name is Felipe Amaro, and I work as a technical and R&D manager for PassionAg. And today I'm going to be talking about the effects of the new oxygen barriers on preservation and predictive feeding value of whole plant corn silage. And I'd like to start this presentation by showing a couple of pictures. I think it's not unusual for us as nutritionists, as consultants, to get to a farm, go to a silage pit, and see situations that look like this. Black, slimy, moldy silage on the top of the pile. Here the picture is not very clear, but you can also see that there is a difference. Besides the black layer on the top, there's even a difference in coloration between this part of the silage that's lower than the parts of the silage that's closest to the top. And that's mainly the effect of oxygen getting into the silage through normal standard polyethylene plastics. Whenever we do use a good quality oxygen barrier, we can actually see results that look somewhat like this, with virtually no black, moldy layer part on top, but obviously that associated to a very good management, right? We know that we have the technology and that can, regardless of what it is, it can be an inoculant, it can be an acid, it can be an oxygen barrier, but we know that's going to work best whenever it is associated to good management. So something that we also need to remember is that silage is the product of a fermentation process. So I think that one of the biggest enemies, if not the biggest enemy of good quality silage, is oxygen. And as I said, whenever we cover or seal silage with a standard polyethylene, there's an amount of oxygen that gets through the plastic into the silo. And whenever that happens, we have this awakening of these bad microbes that are in the silage, and that's going to lead to greater dry matter losses, that top layer spoilage that we saw, and also a loss of nutrients. As opposed, whenever we have a good managed silage that has used a good quality oxygen barrier to seal it, we are going to have this blocking off of the oxygen, so we're not going to wake up these bad bugs in silage. Thus, we're going to have reduced dry matter losses, more preserved nutrients, and also an extended silage freshness. Let's translate it to greater aerobic stability. So we need to know this. Whenever we cover silage with a standard polyethylene, we have all these issues here, losses, problems with mycotoxins, loss of nutrients. And then whenever we do a good job sealing and using a good oxygen barrier, we can actually avoid that issue. But something that I also like about this diagram that is in here is that we have the cows here at the very left here. And that's something that I always say. Our customers are not the distributors, are not the farmers, but are actually the cows, because they are the ones that are going to tell us that we did a good job on making silage. If you have good silage, cows are going to eat more, they're going to produce more, and thus they're going to bring greater returns to the farmers. Okay, talking a little bit about the historical data. The oxygen barriers, the first publication about them came about in about 27 years ago, in 1999, in the International Silage Conference in Uppsala, in Sweden. And then about 14 years after that first publication, 20 other publications were used to build a meta-analysis by Dr. Mike Wilkinson and his colleague in 2014. And a meta-analysis is just a compilation of all this published literature, and it's a very strong piece of literature because instead of being just one trial, now we have several trials and several comparisons. So a few of the findings that these research have found was that, yes, the use of oxygen barriers compared to standard polyethylene, they reduce about 40% of the dry matter loss of silage. They're able to reduce, on average, 70% of the inedible feed of the silage, which is composed of that black, moldy layer on top of the silage. And something that was kind of unexpected is that the silage that were covered with oxygen barriers also had greater aerobic stability, about 2.5 days. And this was very surprising because until then, people only thought that aerobic stability could be improved by the increase of acetic acid. But I'm going to be talking about the reasons why this happened. Okay, so 2014, so this has been, what, 12 years. And in the past 12 years, a lot has changed in the plastic industry. There has been some evolution in the industry. So to list a few things. The first thing that we can say is the discovery and the use of new polymers. Now we have new raw material grades that can be used to produce an oxygen barrier. We have materials that have improved compatibility with polyethylene structures. We have materials that are more resistant to humidity. Some of these materials cannot be, you cannot get water, moisture, otherwise they're going to lose their oxygen barrier properties. And we also have better adhesion promoters, just better glues, right? It may seem simple, but an oxygen barrier is composed of layers. So we gotta have good glue to keep all these layers together so we can get good results. But also have new co-extrusion techniques, such as micro-layer co-extrusion, and also improved protection of that oxygen barrier that is embedded in that plastic matrix. And finally, we also have improved
oxygen barrier retention after handling and stretching. I don't know how many of you guys had the chance to cover a silage pile, but it's not really an easy job, right? Whenever you're on the top of the silo, you stretch the plastic on one side, stretch on the other side. Sometimes you gotta walk across it. So you gotta have good retention of this barrier material after you elongate it and stretch it on the top of the pile. So that's very important for field situations. So we, as a company, started asking this question. What is the effect of these new oxygen barriers and new technologies on silage, right? It's been 12 years since the meta-analysis came about, and not a lot of research has been done. If I'm not mistaken, about 4 or 5 peer-reviewed publications have come in these past 12 years. Compared to 20, right, from until the meta-analysis. So we are lacking some results of these new barriers because there's new technologies available. So thinking about that, we decided to do a small mini silo trial where we use these mason jars, as you can see in the picture, and instead of just covering them with the normal lid that they have, we covered with an oxygen barrier or standard polyethylene. And as you can see in the picture here, we got very good visual results with no mold growth here for the oxygen barrier and very moldy slime silage here for the standard polyethylene. Something that I really wanted to say is that this was a short trial. We only siled these forages for 42 days, which for this kind of experiment is actually very short. We know that the longer the silage is stored, the longer it is exposed to oxygen. So 42 days is actually very short compared to the other trials. And we also used a very challenging crop. And I want to say challenging because this was sorghum, and it was actually of low dry matter, high sugar, and high NDF. We didn't really calculate the ensilability index because it did not have the buffering capacity, but overall it was a pretty challenging forage. And these were the results that we got. We published this in the International Silage Conference last year. And we can see that we reduced dry matter losses by about 45%. We also reduced the inedible silage by about 70%. So this tells us that the new oxygen barriers, they are also protecting silage as expected, but even surpassing the meta-analysis benchmarks that had been established 12 years ago. Remember, this was a short trial with a very challenging forage, and we were still able to get values that were greater than the benchmarks of the meta-analysis. When you look at the silage hygiene, and starting with yeast and mold, we also got very good results where we reduced yeast by about 2 log units here, which is about 100 times. So we had 100 times less yeast, and we're also able to eliminate 100% of the mold. And the combination of these two factors actually leads us to the greater aerobic stability. So that's another lesson for us. The increase in aerobic stability that we get when silages are covered with oxygen barrier are actually coming from this greater silage hygiene that these silages have. You're just blocking off oxygen, so you're just limiting the growth of yeast and successfully molds later then. And again, we're able to validate the silage hygiene performance and surpass the benchmarks set by the meta-analysis. So moving on to the trial that I really want to talk about, we saw that the new oxygen barriers were good in lab scales, but we really wanted to know if the performance had changed in the field. So we partnered with a dairy farm in Brazil. This is about a small to medium farm in São Paulo, about 150 milk cows. And it was a growing herd. I'm going to tell you guys why this is important in a second. But remember, they are expanding. They actually have a project to get to 1,000 cows in the next 8 years. So they're actually expanding their herd. We use just whole plant corn silage, whole plant corn, right, to make the silage. Pretty standard composition here for us in Brazil. And we filled 2 bunker silos. They were pretty large bunker silos, about 60 meters length, 12 wide, and about 1.8 in height. For treatments, we use a standard polyethylene cover, about 150 micron. We use a product that's called Passion Combo, which contains the same barrier that we used in the previous trial. But we also collected some core samples because that's more representative to what the ideal silage would look like. And for ensiling period, we had these collections staggered over time. So we had collections at 64 days, 103 days, 164 days, and 178 days. And that's why it's important to know that this was a growing herd, because I really wanted to have a bigger gap in here from 164 to maybe 210. But this farm had the opportunity to buy more cows, so they actually increased their use of silage in that period. So that's why we only have a 14-day gap here. But regardless, this is the reality. This is a farm trial, so we've got to deal with it. And the samples, they were harvested at 15 centimeters from the top layer for the standard polyethylene and for the oxygen barrier treatment, and then 1 meter from the ground. We then analyzed these samples for the nutritive value. We estimated the milk yield, used 2 equations, the milk 2006 and milk 2024. And then we analyzed the data using the univariate and mixed procedures of SAS. Here's actually a scheme of how we did the collection. So this is the bunker front view. And we collected this 3 samples per sampling time, about 15 centimeters from the top for either treatment, and then 1 meter from the ground for the core. And here's actually what it looked like. So we do have our 3 sampling points here, the core, and then the other 3 sampling points in there. So moving on to the results. I'm only going to be showing the results that were significant. In the abstract, you can have the averages of the ones that were not significant, okay? So I'd like to start by talking about the dry matter concentration of the silage. We actually got results that showed that the dry matter of the silage was reduced whenever we compared standard polyethylene cover with the oxygen barrier and the silage core. What does that tell us? So that tells us that the oxygen barrier actually maintained the dry matter ensiled, which suggests improved dry matter preservation and fiber losses. Remember, this is a farm trial. This is a bigger bunk. So there's very laborious and very hard to measure true dry matter losses under field conditions. But that piece of data associated with this other piece of data here, which is the reduction, right, of ash in the oxygen barrier treatment, actually come together to this piece of information that it means that we have less losses. Bacteria will not eat ash. They will eat the organic matter. So whenever we actually have the degradation of these organic components in silage, we are actually consuming more of the organic matter and actually producing water. So that's why the dry matter goes down and the ash content here goes up. And that's also evidenced by the starch concentration of these samples. So here we have core, standard polyethylene, and the oxygen barrier. And we can see that there was a decrease in the starch concentration of the silage that were covered with the standard polyethylene. Starch, this is corn silage. There's a lot of starch, and starch is highly digestible. It would be the same thing if you're talking about sugars, crude protein. The bacteria will prefer to eat these components that are more digestible than the fibrous component, and that's exactly what we saw. So we saw a reduction of starch for the silage that were covered with polyethylene, and an increase of the fibrous components for the same silage. So Felipe, what's going on? Are we just creating fiber inside of the silo? No, that's not what's going on, right? Remember, those are proportions. So if the bacteria are eating more of the good stuff, more of the digestible stuff, proportionally you are left off with more of the fibers, undigested stuff. So the use of the oxygen barriers, they preserve more of these nutrients, and more importantly, they preserve more of these more digestible nutrients. And that's possibly is going to have an effect in the production of the cows. I guess we're pretty used to this, but cow trials, feeding trials are usually pretty expensive, especially these days. So there are other ways that we can try to at least estimate how much milk we can get from applying a technology. In this case, we use the Milk 2006 and Milk 2024, which are two equations that are used extensively in the corn hybrid selection programs that actually show the potential of these hybrids to produce milk per ton of that forage. So similarly to that, we just decided to compare these treatments inputting the results that we got into these two equations. And I just brought the two of them here just to show you guys that this is a more simple equation. It's an older equation, and this is the updated equation. Some people are not still used to the Milk 2024, so that's why I brought both. But there's a very important difference here. Because this is a simpler model, an older model, it actually overestimates milk production when we compare it to the Milk 2024, which is closer to the modern cow and closer, it's closer to the parameters that we can get these days. But regardless of the model that we use, we still got an increase of about 2.7 to 3% in milk. So this actually tells us that yes, the silates that were covered with an oxygen barrier, the new ones, they have the potential to produce more milk just because we have more of these readily available nutrients ready to be digested by the cow. And similarly, I just wanted to show these ones here because that's really not well known, but the same way that we have the Milk 2006 and 2024, we also have the Beef 2019, which is also an equation that's going to give the kilograms of beef per ton of forage and also estimates an average daily gain. And then again here, we saw greater gains for the silages that were covered with oxygen barriers. Well, as for the conclusions, the new oxygen barrier products, they still need continued testing. Right? These were only 2 trials. I think that we still need to understand a little bit more of how these new technologies play a role in silage quality. But they were proven efficacious under these challenging and silent conditions, under short and long-term periods, but also under lab and field situations. Also, the oxygen barrier that we tested, it improved the silage nutrient preservation and the predicted milk and beef yield. But we acknowledge that we should have further research that should be investigated animal performance now using cows doing a proper feed trial, but also something that's very concerning these days is the easiness of use of the technology, right? I guess the labor shortage is a big issue pretty much everywhere in the world that you go. So there's very little people that want to do agricultural work. And I think everything that we can do to make the life of the farmer easier, we should do. And I just want to finish with this video here. This is a beautiful end of the day in Brazil. This was actually the silage pile that we used for our trial. Again, this was a pretty big silage pile, as I said, 60 by 12. And you can see that in a matter of just a few seconds, we're able to cover a third of this farm bunker just because there is new technology already available, and we should be finding ways to compare these new technologies so we can show to the farmers that it's worth it and they should lay use of these technologies. This one is a product that actually has the oxygen barrier on there and already has the OB on top. And with that, Thank you, and I'll be glad to take any questions.
Great, so thank you for the nice presentation. Maybe I will start with the first question. The problem, especially in the Czech farmers, but I think it's everywhere the same, is the recycling of this plastic, because it produces a huge amount of the waste and most of it finish on the landfills. So how is it with your material?
Perfect. Yeah, so this material is recyclable as long as it's clean, right? And we know that this is probably one of the biggest challenges of plastic for silage. We, as an industry, we're still struggling to try to find polymers that are maybe biodegradable, that also have a good oxygen barrier. That's the next step. I'm not sure when we're gonna get there, but we are trying to get there. There's also some other products that try to use less plastic, combine all of these materials into one, for example, but still the gold standard is always to use a very thin plastic under and then the other one on top, just because it's going to cling better to the top of the silage, and then you're going to have a better sealing effect. But yes, we are aware of the plastic concern. These products, most of them are recyclable, but they need to be clean.
There's a trouble. Fine, thank you. So we have another question.
Thank you. Please, shall you provide us with the parameters of the plastic foil? How many microcentimeters of the oxygen are going through on the permanent top layer, or also the transparent, the soft layer, in temperature 21 degree and air press 1 bar?
Perfect. So this is a very good question, very technical question. And the short answer is that for those specific characteristics, I'm not going to have a number for you. Those are very standard methods that we use to test our products. So for example, for our oxygen barrier, the 45 micron, the thin one, we have an oxygen transmission rate, an OTR, of about 0.4 ml, cubic centimeters, per square meter per day. But that's under 50% humidity and under 23 degrees Celsius. So if we're going to talk about maybe more extreme temperatures, we'd have to perform more technical trials and assays to try to establish that. But that being said, remember that I said that the barriers, they are built in layers. So the layers actually help to protect the oxygen barrier layer that we have on the product. So it shouldn't change a lot, but that's just me giving you like a guesstimate, because I wouldn't really be able to say for sure.
Okay, so thank you, Aleš, for the question, and Reinhard has the second one.
Felipe, thanks for this amazing presentation, and two questions. One is, can you spend a few words about the new raw materials that are used for this oxygen barrier films? And the second is, I calculate this top layer in amount, it's approx 40% of the whole bunker. And can you explain us the economic advantages for the whole mass and this surplus of good protection?
Perfect, thanks for the question. So to answer to your second question first, right? So do I have an economical number to give you guys? And you already calculated it's about 40%. So historically, we say that oxygen has an effect on silage in the first meter from the top towards the center. So obviously, silage piles that are shorter, they're gonna have a greater percentage of their silage, the total silage, affected by oxygen. So for me to give you any specific number, I can't, because that's gonna vary. If you, for example, in the US, we have forage bunkers that are over 5 meters tall. And then that's only about, what, 20% of the silage. If we're talking Brazil, sometimes we actually have silage piles that are less than 1 meter tall. So we're actually talking about the whole silage being compromised. So that's going to vary widely where you're talking about, and according to the size of the pile, but also it depends on the density of the silage, right? We say 1 meter as an average number, but we know that silage that have a greater density are going to have a greater difficulty for the oxygen to get into it. So there's just a lot of things that we need to consider. But the short answer would be this. We need to know the size of the pile and see at least how dense it is so we can do this right calculation. But apart from that, something that I did not mention is the homogeneity of the silage phase, right? And that's regardless of having 20% or having the whole pile compromised. If you have that layer compromised, the 20%, you're still mixing that in your forage wagon, in your TMR wagon, and that feed that's less nutritious is also getting to your cows. So that's also another danger that we should be able to calculate in specific situations. Your first question, I'm sorry. Yes, raw materials. For raw materials, I guess the biggest shift was using, before we were using oxygen barriers that are made of polyamide, which is just a older polymer that has an OTR that's a little bit higher than the newer one. The standard today is EVOH. But personally, there are oxygen barriers that are made with polyamide that are actually superior than EVO8, because even within the raw materials you can have different grades. So if you have a very low grade EVOH, which is maybe the newest raw material that would probably provide you more protection, but you have like a highest grade polyamide, you can still have a better product over here. But mainly we are using polyamide and EVOH.
Okay, so thank you, Filippo, for very, very detailed answer, but we have 20 minutes delay, so very brief question and very brief answer now. Last one, yeah? Sorry.
Yes, thank you very much for the presentation on the oxygen barrier. I just want to check from you, because I've seen in many cases, this oxygen barrier is used in maize silages. I just want to check, is it because of the compaction density, so that they prefer to be used in maize? And then I just want to find, can it also work with grass silages? Like, for example, we guys from South Africa, we are working on grass silages with the smallholder farmers because of the drought that sometimes is challenging us there. So I just want to check if possible, can we have something like this kind of a film under small scale situation where we can apply it and use it for the farmers to improve the silage quality. But I think somehow the packing density might be a challenge. Thank you.
Okay, to try to short answer that, yes, you can use oxygen barriers for pretty much any ensiled feed. You can use it even for high moisture grains. We have several farms in Brazil that use it in real hydrated corn, for example, or high moisture corn in the US. And you can use for grasses as well. In the UK, you have lots of farms that do mostly grass silage, and they use oxygen barriers. They're going to work the same. And then for a smaller scale, we're still trying to work and understand how that would play a role, maybe to try to help these smaller producers to also get good quality silage. But we can talk more later, okay? Thank you.
Thank you, Filippo. And we have the third presentation in this section. That's Ms. Borkowska, sorry. So I'd like to ask you to come, and the presentation will deal with the novel Lactobacillus buchneri microbes. So the stage is yours, and you can introduce your presentation.
The main focus of my presentation today is the recent reclassification of Lactobacillus buchneri group into 2 subspecies, and I'll talk about the efficacy of the new strain NCIMB 30673 in enhancing aerobic stability of maize silages. Right, so very briefly on the role of the buchneri in silage presentation. I'm sure everyone in the room already knows it, but they've been used as silage inoculant for a couple of decades now. The mode of action is through the generation of antifungal agent, acetic acid, which suppresses the proliferation of opportunistic yeasts and molds, and that prevents the generation of the heat in the silo upon opening, thereby enhancing aerobic stability. And that then leads to reduction in dry matter and quality losses during the feed-out stage. So what is the biochemical action? What is the biochemistry behind it? Is the buchneri are classified as obligate heterofermentative bacteria, meaning they don't use glycolysis to break down sugars into lactic acid only. They use phosphoketolase pathway and then break down sugars into lactic acid and other products. And one of the other products is the antifungal agent acetic acid. But on top of that, they have the ability to further metabolize the accumulated lactic acid into acetic acid, propanediol, but at the cost of producing CO2, meaning increased dry matter losses during fermentation, but hopefully the enhanced aerobic stability and the minimized losses during the feed-out stage should more than compensate for these losses. Now, moving on to more interesting stuff. In 2020, a Japanese research group published this paper in which they characterize a newly found strain of Lactobacillus buchneri called SG162, which they had isolated from rice grain silage. And in this paper, they pretty much characterized the strain based on its physiological, biochemical, and genetic characteristics. They did a bit of comparative genomic analysis of the strain to some of the other strains, which are out there. They are listed in this table right here. And upon completion of these analysis, using ANI and DDDH, they noticed that some of these strains share more of the DNA than with the other strains used in this analysis. So both of these analyses clearly separated the buchneri strains used in this study into 2 distinct groups. They were called groups A and B, and they proposed that these 2 groups be separated or reclassified into 2 subspecies. So at the moment, we've got 2 subspecies, one being the buchneri subspecies buchneri, and then since all of the strains used in this analysis that fall under the other subspecies were isolated from different silages, they called this subspecies Salagiae. And what's interesting is around the same time, we were completing our own comparative genomic analysis of some of the buchneri strains that we have in our culture collection. So we had 27 strains that we used in our analysis. And similarly to the Japanese research group, we found that these strains can be separated into 2 distinct clades, shown here and here, in this heat map based on the FastANI analysis. So in blue, you've got the strains that share about 97% of the DNA, and then 99 is denotes where the strains are more closely related. And now we know that these strains fall under 2 different subspecies. And one strain that sits in the Salagiae clade was strain NCIMB 30673, which seemed to be quite interesting to us based on some of the characteristics of it, the way it grows, but also we were unfamiliar with the Salariae subspecies is not something that we have in our products. So we picked an interest and decided to do a study on to test the efficacy of the strain to improve aerobic stability in maize silage in order to evaluate the effectiveness of the strain to be a successful silage additive. So materials and methods used in the experiment. We had whole crop maize of about 37% dry matter, which we collected from the field, transported to our lab for ensiling. Upon arrival, the material was homogenized and then split into two groups. So one group was treated with water only, that's our control. And then the other pile, LB, we treated with NCIMB 30673 at a target application rate of 1 × 10⁵ CFU per gram of fresh forage. So these silages were then ensiled in glass jars at a packing density of 180 kilograms of dry matter per meter cubed, and then stored at 20 degrees constant for either 28 or 99 days. Upon silo opening, we homogenized the material once again, and then we looked into fermentation quality parameters, so pH, microbiology. We looked into acids and alcohols by means of HPLC, obviously aerobic stability, since that was our main interest. And then lastly, the data was analyzed for statistical differences, and P was defined as 0.05, or lower than 0.05. So what did the results look like after 28 days of fermentation? So both control and LB silages achieved a stable pH of 3.81, meaning both were well fermented. The LB silages had significantly higher population of lactic acid bacteria compared to control, and that resulted in higher levels of lactic acid in the treated silages. Acetic acid was also elevated in treated silages compared to untreated, but they remained relatively low. So we had about 1% of acetic acid per dry matter in control and 1.5% in treated silages. As it turned out, these levels of acetic acid were insufficient to suppress the yeasts, and that led to low aerobic stability in both control and treated silages, which had spoiled just after 1 day into aerobic stability test, which was disappointing to see. Now, after 99 days of ensiling, lactic acid bacteria population remained to be higher in treated silages relative to control, but the levels of lactic acid had significantly declined since day 28 and were significantly lower relative to untreated silages. So that resulted in a slight increase in the pH of the treated silages to pH 4, meaning it was still well fermented. Now, acetic acid levels significantly increased in LB silages relative to untreated, and so did 1,2-propanediol, which is very consistent with the heterolactic fermentation associated with the Buchneri. And the elevated levels of acetic acid in LB-treated silages successfully suppressed the undesirable yeasts, which were just above the level of detection. So the level of detection was 0.6, and the levels was 0.66. Whereas in the control silages, the levels remained to be very high. As a consequence, the aerobic stability in LB-treated silages was enhanced to 6.88 days, which is when we stopped the experiment, whereas the stability in the con silages was only 2.1 days. And also the aerobic losses were reduced in the treated silages relative to control. and this is what the silages looked like after the aerobic stability test. So we have visible spoilage here on the surface of cone silages, but the LB-treated silages remain to be nice and fresh. So in conclusion, in this trial, both cone and LB-treated silages showed effective fermentation, dropping the pH to below 4 by day 28. But the LB silages were characterized by higher population of lactic acid bacteria, higher acetic acid and propanediol, which are consistent with the heterolactic fermentation associated with the Buckneri. Now, ensiling time matters. I think we all know this. So after 28 days, acetic acid was too low to suppress the yeast, leading to lower aerobic stability in both treated and control. But by day 99, the full inoculant benefit emerged with the Buckneri treatment extending the aerobic stability to 6.8 days versus 2.1 days in control silages. And also the aerobic losses were reduced in treated silages relative to untreated. And these findings clearly demonstrate that L. buckneri subspecies Salargii and CIMB 30673 have a potential to be a successful silage additive for improving aerobic stability. And that is everything from me. Thank you for your attention, and I welcome any questions you may have.
Great, thank you for the presentation. And now there is a time for a few questions, but I think one question should be enough because otherwise we would have higher delay. So is there any question? Okay, there is one.
Thank you for the presentation. My question is, why did you choose 28 days? Because usually it is known that heterolactic lactic acid bacteria, they have the acetic acid production after like 7 to 8 weeks.
So this was clearly an informative piece of work. We were just scoping out, looking at what the silages, what's inside the silages after 28 days. So there wasn't any specific reason other than just curiosity.
Great. So thank you for the
very much.
Answer. And now we have a time for the next online presentation with our Chinese colleagues, so hopefully the connection will function. So Mr. Wang, or Mrs. Wang, I'm not sure, should present the next lecture concerning the different treatments of fermentation quality and greenhouse gas emissions of inside wheat straw, so another straw. So I can see there are muted microphones in Chinese side. Could you hear us?
Hello.
Hello, we can hear you. Could you just switch on your camera so we could see you?
Okay. Okay.
Perfect, we can see you.
Okay.
So, hello.
Now I will still start my report.
Great, we can see your presentation, the first slide.
Okay.
So, okay, you can start. The stage is yours, eh?
Okay, thank you. Dear everyone, I'm Jidong Wang from the Zhengzhou University, China. It's my great honor to present our team's research on the effects of different treatments on fermentation quality and greenhouse gas emissions of insulated wheat straw at the 20th International FORAGE Preservation Symposium. Silage as an efficient and economical feed preservation technology plays an important role in the sustainable development of the livestock industry. However, the utilization of wheat straw as a significant refuge resource still faces neutral utilization of wheat straw silage. I will now present a detailed report on the topic. I will report in the following three parts in order. The global silage feed market continues to expand. Currently, the global annual production of silage feed exceeds 1.2 billion tons, indicating robust development potential for the industry. Silage is a technical approach that utilizes an anaerobic environment and microbial fermentation to preserve feed. This technology enables the utilization of straw resources as feed, providing essential support for the sustainable development of animal husbandry. Wheat is the world's largest staple crop and core commodity in the international trade system. The straw generated after harvest serves as a crucial source of roughage for ruminant livestock feeding. From a material properties perspective, wheat straw is relatively soft, making it easier to compact and aerate during ensiling. It also contains moderate levels of WSC along with abundant cloud fiber, neutrally meeting the fundamental requirements for silage fermentation. The wheat straw silage industry faces two major critical challenges that directly hinder its sustainable development. First is the issue of greenhouse gas emissions. Agriculture accounts for 18.4% of global greenhouse gas emissions. The silage fermentation process continuously releases three major greenhouse gases: carbon dioxide, methane, and nitrous oxide, significantly aiding carbon emission pressures in animal husbandry, and addressing this issue has become a priority. The second risk is feed mode contamination in production. Parcelling of silage allowing oxygen to enter, promoting extensive proliferation of aerobic microorganisms, which directed fermentation quality and endangers livestock health and production safety. The primary objective of this study is to evaluate the impact of different treatment methods on both the fermentation quality of wheat straw silage and greenhouse gas emissions. The study selected two types of activities, RB and silage, and employed various bacterial strain combinations in several experiments with three objectives. First, to identify the optimal silage treatment protocol. Second, to enhance the nutritional quality and aerobic stability feed. Third, to reduce greenhouse gas emissions during the ensiling process. The second section details the experimental design, including the different treatment groups and research methodologies. This study established six treatment groups to construct a well-defined variable control system. The first group served as the blank control group, where wet straw was directly inserted. Two groups of REB treatments at least either the independently isolated and secured this strain of the commercially available FG1 strain, respectively, to compare the efficiency between the novel strain and the established competitor strain. Additionally, separate cellulase treatment groups were established along with combination groups of this with cellulase and FG1 with cellulase to clarify the differences in efficiency between adaptive use alone versus combined application. The third section presents the results and analysis. We first focused on the core indicator of fermentation quality. As shown in Figure 1, all groups exhibited content trace during the silage fermentation process, a sustained decline in pH, continuous accumulation of lactic acid and ammonia nitrate, and gradual increase in WC content, all aligning with the fundamental scientific principles of silage fermentation. Upon entering the Arabic partial phase, oxygen purchase activities, the activity of Arabic microorganisms, further decomposing organic acids and driving an increase in both pH and ammonium nitrogen levels, thereby confirming the biochemical changes occurring during mode contamination. Results demonstrated that the treatment group included with our selected RB, these exhibited significantly super fermentation further compared to both the country group and other treatment groups. The crude protein content decreased significantly throughout the fermentation process, a change consistent with the general principles of silage fermentation. During fermentation, microorganisms degrade proteins in their feed to meet their metabolic requirements. The count of both NDF and ADF decreased in all addictive treatment groups, demonstrating that in correlation with RAB combined with cellulase effectively degrades fiber composition in straw. During the airbrake partial phase, continuous loss of dry matter increased the relative proportion of CP, where the percentages of NDF and ADF slightly recovered by remained significantly lower than those in the control group. Figure 3 illustrates the dynamics changes in microbial populations during the fermentation process and the aerobic partial phase. During silage fermentation, beneficial bacterial continually increase, and once the dominant microbial community forms, it directly suppresses the proliferation of harmful microorganisms, establishing a stable microbial foundation for high quality fermentation. Upon entering the aerobic exposure phase, oxygen alters the microbial environment, disrupting the established inhibitory balance and reversing the microbial dynamic, which leads to renewed growth of harmful bacteria. Figure 4 is the dynamic changes in greenhouse gas emissions throughout the fermentation process. Silage inherently significantly reduces greenhouse gas emissions, making it a feed that offers both production and environmental benefits. Comparison of data across treatment groups shows that most active treated groups demonstrated markedly superior emission reduction effects compared to the control, demonstrating that the addition of probiotics or cereals further enhances the environmental value of silage. These two polls illustrate the differences in alpha diversity between bacterial and fungal communities at the OTO level in silage samples. Upon completion of silage fermentation, significant differences in bacterial and fungal diversity were observed between the various active treatment groups and the control. During the aerobic exposure phase, those diversity become further widened across all groups. Figure 8 clearly illustrates the structural distribution of bacterial and fungal communities at the genus level, allowing us to intuitively identify the core patterns of microbial community successions. The genus lactate plant biocells repeatedly achieves absolute dominance after inselling and maintains this dominance throughout the entire aerobic expression period. This directly drives a certain decline in the pH value, which inhibiting the proliferation of harmful microorganisms and laying a solid foundation for fermentation quality. The signation of fungal communities exhibits determinate stage-specified dynamics during the ensiling phase. Candida species dominate, where the abundances of alternaria is significantly reduced. Upon entering the aerobic exposure stage, Wilhelm Messers and Pitchers replace the original microbial groups as dominant species. This succession pattern further dominates that the addition of RAB additives can restructure microbial community composition and selectively optimize the fermentation environment. This study researched the dramatic changes in fermentation quality and greenhouse gas emissions during ensiling and aerobic exposure of withdrawal under different additive treatments as a home fermentation strain. Lactate plant biocells planter repeatedly produces acidic substances that lower the pH. First, it enhances the evidence of beneficial microorganisms while inhibiting the growth of harmful contaminants, thereby improving overall fermentation quality and stabilizing the silage during aerobic exposure. Second, the dominant growth will be directly suppresses the proliferation of gas-producing bacteria, reducing their aerobic respiration and producing metabolic activities, ultimately decreasing emissions of the three greenhouse gases. This conclusion provides a valuable approach for green processing of straw as feed. We extend our gratitude for your valuable time in attending our presentation. Once again, thank you all for your attention and welcome to General University.
Thank you, Idunk, for the talk. So now is a time for one or two short questions, if you have. So maybe I will start. So can you tell me, I just didn't mention what was the dry matter content of your straw silage. What was the content of the dry matter in the silage from the straw you used? Can you understand me?
I can't hear clear.
Okay, so I try to ask you again. So what was your dry matter content in the silage from the straw? Or how much water did you add to the straw before the silage making?
You mean water?
Could you hear me? Okay, so there is probably some trouble with the communication. So.
You mean water after inside or before inside?
Okay, so we can leave it for another time. So probably the discussion, I will skip the discussion.
About 65%.
Okay, so maybe I haven't mentioned this. Okay, anyway, we have a little bit delay, so sorry for this shortage of the discussion, but because there are some troubles with the communication, I will skip the discussion in your case. Sorry for that, and we will continue with the last presentation, if you don't mind, yeah? So thank you again.
Okay, thank you.
Right. And I will use the rest of the time, and I'd like to invite Miss Pieper with the last presentation in this block of lectures. And the name of the presentation is Strategies for Production of Alfalfa Silage. So the stage is yours, and hopefully we will be able to open the presentation and start. Great, it looks promising.
Hello, everybody. I am the next presenter. I am Laura Pieper, and I am directly between you and lunch. So I'll try to keep it short. So my topic is some strategies for the production of alfalfa silage. And there are some common strategies, but also some for the more difficult ways. Can I have the presentation? Okay, thanks. So alfalfa is considered to be the queen of forage plants because it has a very high protein content, between 16 to even above 20% of the forage. And also it has a high nutrient content, high mineral content, high vitamin content, is very palatable. The cows just love it. They just love it. And it's a very good addition to the forage, to the TMR. But what makes it a very good plant for the forage and for animal nutrition also is very difficult for us to ensile because of the high protein content and high mineral content. So this is what I'm going to talk to you about. So when we look at some properties of alfalfa, we can see that, for example, here we have ryegrass, and the sugar content of ryegrass, we have a high sugar content and a low buffering capacity. In comparison, in alfalfa, we have low sugar content and high buffering capacity. And this is what makes it very difficult for us. So just as a quick reminder, the buffering capacity is the amount of lactic acid that we need to decrease the pH of the forage to 4.0. And it depends very much on the species, on the harvesting time, and also on the degree of contamination with soil. So if we use sugar and buffering capacity in combination with the dry matter, we can calculate the fermentability coefficient. And the fermentability coefficient, if it's above 35, we consider it as an easy to ferment forage. And if it's below 35, we consider it a difficult to ferment forage. And if we look at the same species that I presented you before, we can see that ryegrass has a high fermentability coefficient and alfalfa has a low fermentability coefficient, so is considered difficult to ferment. So what can we do to improve this fermentability of alfalfa? Well, we can cut it at the optimal time. We can try to avoid soil contamination because I told you it contributes to buffering capacity. We can use wilting. Obviously, we need to chop it very well and we need to pack it very well. And also we should add lactic acid bacteria. So I just want to mention those two. If we look at the natural microbiota that is on the forage, we can see that approximately 10 to 1 million lactic acid bacteria are on the forage. So it's very variable what you find on the forage, and sometimes it's too few. And just because you find lactic acid bacteria doesn't mean that these are very effective in fighting the other microbiota that you find on the forage. And that's why it's always a good idea to use highly effective lactic acid bacteria to use all the sugar, because especially in alfalfa silage, we need it very much. We need lactic acid production and not other fermentation pathways. So the next strategy is wilting. And you all know that wilting helps us in ensiling the forage. And if we look at, if we wilt the forage to 35% of dry matter, we can see that we can increase the fermentability of alfalfa above the threshold of 35, and we have a forage that is easily fermentable. So in most cases, if you can use wilting, just adding lactic acid bacteria is going to be sufficient to make a good silage. Obviously, you also need to pack and cover it very well, as you know. But sometimes it's not possible to wilt to the ideal amount of dry matter. So this is data from a laboratory in Germany where alfalfa silage samples were submitted. And you can see that 20 to 30% of the samples have a low dry matter, even below 25%. And these silages are at high risk of spoilage and of butyric acid fermentation, so to have bad quality. So what are some strategies for low dry matter alfalfa silage? So the first thing is the addition of fermentable carbohydrates. We can add molasses, and the molasses can contribute to the dry matter And also it gives the bacteria some feed to produce lactic acid. And also it adds to the nutrient content of the forage and is available to the cows at the end. And the next one is the addition of acids. So in here, my colleague Jutta Zielke, she added lactic acid, this is the blue line, to minced alfalfa, minced fresh alfalfa, and she saw that you needed about approximately 50 grams of lactic acid in order to decrease the pH from 6.5 to 4.5. But then this is not a linear relationship. You needed approximately the same amount to decrease the pH from 4.5 to 4. So a lot more than in the first time. And the same relationship is true if you use formic acid. Just that the formic acid is a stronger acid, and in general, you need a little bit less of this. So then she also tried other acids, and you can see the strong acids, you need very few of them, but for the weak acids, you need a lot of acid in order to decrease the pH to 4.0. So in theory, we could decrease the pH with the acid, and then the natural bacteria would come in and use the sugars, decrease the pH a little bit more, and then we have a stable silage. However, if we have a weakly populated silage, as I showed you before, can actually happen, then it could be that the bacteria are not sufficient to decrease the pH even further, and you would have late spoilage after a couple of weeks. So the hypothesis is that you use formic acid in combination with lactic acid bacteria in order to effectively ferment the sugars that are available and decrease the pH to very low amount, and then you have a stable silage. And that was the objective of the studies. So we had 2 studies being done in official testing stations, one with 18.8% dry matter and one with 25% dry matter, and a very low fermentation coefficient, very low sugar content. So this is difficult to ferment forage. We had a duration of 90 days and tested dry matter loss, pH, ammonia, butyric acid, lactic acid, acetic acid, and also biogenic amines. So we had different silage additives that we tested. We had homofermentative lactic acid bacteria. This is our product Biosil, which is based on Lactobacillus plantarum. Then we had buffered formic acid, which is 75% formic acid. And we also had molasses that was tested. And these are the groups. So we have control, bacteria only, then bacteria plus molasses, formic acid, the buffered formic acid, and buffered formic acid plus bacteria. And these are the results of the first trial with 18% dry matter. And you can see that the silage was really bad. So we had 20% dry matter losses, pH of 5.4, very high ammonia content, very high butyric acid content, and very high biogenic amines. And unfortunately, just the bacteria alone could not help in improving the silage quality to a very significant amount. And that's why we also don't recommend to just use bacteria in such difficult conditions. However, if you used buffered formic acid or bacteria plus molasses, you could improve the silage quality to something that you could actually feed to the animals. But the best version was the buffered formic acid plus lactic acid bacteria, where you had the lowest values for all those parameters that we measured and a very excellent silage quality. So here we have lactic acid and acetic acid in those treatments. And you can see that we had a low content of lactic acid in the first 2 groups, but then a higher content of lactic acid in the two groups with the buffered formic acid, and a very high content of lactic acid in the group with the molasses. Obviously, because you have a lot of food for the bacteria to produce lactic acid. But on the other hand, we have a high content of acetic acid in the control group and much lower contents in the other group, with the lowest contents in the group with the buffered formic acid. And the same was true for the second trial, where we had much better quality in the beginning, but also high ammonia content in the control and high biogenic amines in the control, and no very good effect of just lactic acid bacteria. But the same, what we saw in the first trial, with good effects of buffered formic acid and good effects of lactic acid bacteria plus molasses, and the best effects when we combine bacteria plus buffered formic acid. So these are some recommendations that we saw from, that you can use the buffered formic acid in combination with bacteria, depending on the dry matter of the forage. And always keep in mind that you need to apply those silage additives separately. So you cannot mix them in one container and then apply them. They need to be in separate containers. It also works for if you want to mix molasses with buffered formic acid. So if you have a good source of molasses, you can use that. And you need also various amounts depending on the dry matter of the forage. And you can also use it for different forages that are difficult to ferment, for example, clover or wet whole crop silages. And also, if you want to use molasses, there's also various amounts that you could use depending on the dry matter. So, how do you put that on the plant? And sometimes it's very nice to see what kind of creative ideas people have, the farmers have, and oftentimes when we talk to researchers, they say it's so difficult to apply two different silage additives. But I think you need to allow the creativity for the farmer to decide if it's too difficult. Because the advantage on the silage quality is actually there. If you have a very good silage quality, it's worth doing the extra step. So you can, for example, carry the Amasil container like this in the harvester. You can mount dosing equipment in the front of the tractor if you have a baler. Here we have a picture of two different dosing equipments on the same harvester. So it's also possible, and it's been done in practice. So this is not something that is only happening in the lab. Here again, you can also apply bacteria or silage additives on the swath, which is also possible. So as a recommendation, you could use, for example, the bacteria in front of the machine and then use the acid in the back just before it exits the machine, so that you don't have the acid working within the machine. So in conclusion, in most cases, if you're able to wilt your material, just wilting and lactic acid bacteria is going to be sufficient to make good silage quality. But if you cannot wilt, you can, in low dry matter situations, you can use buffered formic acid in combination with lactic acid bacteria, and you get the lowest losses and very good stability, very high quality forage. Alternatives to that solution would be just to use the molasses plus lactic acid bacteria, or just the acid, buffered formic acid. And there are options to dose that on farm, so yeah, it is technically possible. Okay, and with that I'm done, and I'm open for questions. Thank you very much.
Okay, so thank you, Laura, for your presentation. And maybe I will start with the first question concerning the fluid, the silage fluid, which is released from the wet silages. Did you measure it? Because it can be also a big trouble.
Yes, it is a big trouble. This is a problem, so I would not recommend to use silage with 18% dry matter. You have problems with the effluent, and this is a big loss. Yeah. If you use bacteria, you have less fluid being produced. And if you have, for example, with molasses, you can increase the dry matter a little bit, but still this is a problem, yeah.
All right. But there is another question, Aleš.
Thank you, Laura. In the slide of 17, wasn't mentioned the dosage rate of the Amasil Na for the dry matter 25.
17.
17, I hope. So. 27.
The Amasil?
Amasil dosage rate, yeah. So it has to be separate dosage rate on the cutter, separately bacteria and separately Amasil.
Yes, this is very important because if you add them together in one machine or in one container, the bacteria are going to die very quickly. Also with the molasses, you cannot mix the bacteria with the molasses because the osmotic pressure is too high.
Okay, so there is another question.
Thank you for this excellent presentation, Laura.
Thank you.
I would like to add something what I think is very sad. I live in Hungary, and we have very dry and hot summer during the last 5 years. So it seems to be that we will lose the alfalfa, the lucerne, in our country or some part of our country. I just mentioned that it's a very serious and critical process in the south part of Europe, that in some region the lucerne will be disappeared soon. I think Serbia, Croatia, and the southern part of Europe has similar situation. I'm very sad because the lucerne is the queen of forages, so I'm a very profitable and is very good protein source. And I have a question: how can you use the molasses? 15-20 years ago, I had a trial with molasses, and it's not easy to apply because it's very sticky. Even if you dilute. Can you give some suggestion about it? How can we use?
Yeah.
Thank you.
Yeah, I think nowadays a lot of farmers switch to the acid variant because sorry, the application of molasses is not very easy. It's so sticky, as you said, and you need very strong pumps, and it's also the handling, especially if you're in the fall and it's cold, then it's even more viscous, and it's basically you cannot handle it anymore. So this is difficult. For example, you could use the combination with the two, the acid and the molasses, or also I heard that there's an option to have urea in the molasses, which improves the fluidity of the molasses. But certainly handling of molasses is not that easy.
Fine, thank you. And the last question.
Dr. Laura, thank you for your presentation, very nice. Based on your data, it's clear to me that LAB is supposed to be one very fixed answer and a recommendation.
Yeah.
But the question is, what would be the rationale to decide to put molasses or either the buffer formic acid as the combinant with the LAB?
Yeah.
Because both the results were good, right?
Yes, they were very good. I would say, as I mentioned, the molasses is more difficult to handle. And also the volume of the molasses that you need to move and have ready on the field is also different than the acids. This is one point. What I did not show is that you have a lot of energy in the molasses. So it could be that you have remaining sugar in your silage and that you have a decreased aerobic stability.
Okay.
Yeah, but in general, the system works really well, and you have a high palatability with both variants. No negative effects on the cows.
Okay, thank you.
Great. So thank you for the last presentation and answering the questions. And now we will receive some information concerning the lunch and the continuing of the conference.
Hello. Yeah. So lunch is at the same place like yesterday. So we have almost 25 minutes to get the lunch, and we met here in 2 o'clock. We will continue with this online presentation, Marketarina. Yeah? Good appetite.
can start section number 2, nutritional value of silage and precision feeding. And first presentation now will have Professor Markéta Rinne, and the aim of this presentation is effect of additives and moisture level on crimp and siled faba bean composition and degradation of anti-nutritional factors. Markéta, you can start.
Okay, thank you very much, and hello everybody, and I'm really sorry I was not able to make it to the conference physically, but we are in the middle of the experimental silage making season here in Finland, so I've been very busy in the fields and sampling, but luckily I have now the chance to present this experiment to you online. So now we are talking about this experiment was funded by the Finnish Organic Research Institute, and the motivation was to increase the protein feed self-sufficiency, particularly for monogastric farm animals like pigs and poultry. And this protein supply is a very burning issue in the whole European Union. Here in the graph you see that we do produce quite a lot of rapeseed and sunflower protein for livestock feeding. But when you look at the first bar, it's the self-sufficiency of soy-based protein, and it's very low. So we import about 30 million tons of soybean protein annually from overseas, and then particularly for organic production, it's a big problem to be able to provide the animals with protein supplements. So that's why we looked into the faba bean in this project, which is a robust legume and produces quite well also in marginal conditions, even in different regions of Europe, and how to use that one then for the protein supplementation. And then to preserve the beans, we used crimping and ensiling. This is a procedure that is commonly used in ruminant industry for cereal grains. And it's a good alternative in humid conditions compared to the drying, so then you can skip the investment and running costs of the dryer. So then we used crimping and ensiling in this. It's not very commonly used in pig and poultry side. They prefer dry feeds, but this could be an alternative, particularly in organic production. It could fit in the feeding systems or in the liquid feeding systems for pigs. So we saw some potential there. And the additional benefits for the crimping and ensiling is that there's less weather dependency and a wider harvesting window, which is of course helpful in many cases. As we know, the challenges the bad weather can cause for feed production. And particularly in this case, we were interested in the modifications that happen during fermentation, because these faba beans contain some anti-nutritional factors, and also the digestibility of the feeds can be improved during fermentation. And then later maturing and higher yielding varieties can be used in this system, and also the capacity of preservation is higher than in the drying. But then we had another novel component here in this project. So we combined this bean preservation with a green biorefinery approach. And in that part of the project, we started with this clover-dominated grass material, and it was fractionated into liquid and solid fractions using this pilot scale screw press. And in these figures you see, in these photos you see how the biomass then resulted in the solid fiber-rich fraction, and then in this liquid fraction which contained most of the soluble nutrients in the grass material. We kept the liquid in closed buckets for 2 weeks in room temperature, and that resulted in precipitation of the true protein to the bottom of the buckets, and then there was this brown juice, or grass wee, as we call it in this project, in the top. And this grass wee we collected and used it to mix it with the beans in this experiment. And here is, then we had 2 ways to produce this grass wee. We had some buckets where a natural fermentation took place, and then in some other buckets we added a formic acid-based additive. And if you're interested in this grass part of this project, then last week that work was presented in the Nordic Feed Science Conference, and you can find that abstract at the website of that congress. So we had these 2 different types of grass wees, and both of them had a very low dry matter content, about 4%, a low pH, not so much crude protein, and none of it was in the form of true protein, because that had been precipitated in the bottom. But also the proportion of ammonia nitrogen was very low, so the protein was not degraded to that extent. And the one with natural fermentation had a high lactic acid concentration, 10% of the dry matter, while the one that received the formic acid, that had restricted the fermentation, so there was hardly any fermentation acids present in it. Okay, then the faba beans. Here you can see some pics about harvesting of the faba beans. They were already quite mature at the time when they were harvested. And then we took the beans to a local dairy farmer that used this crimping method to produce his own feeds, and we ran the beans through his crimper mill so that the crushing of the seeds was done at the same way as in practice. And the treatments, we had altogether 9 different treatments. This graph here shows the different treatments. So those 2 wees that I showed earlier on, they are the ones in the middle. But then we had a negative control, which was tap water, and then a positive control, which was formic acid mixed with tap water. And then all those different treatments we used at 2 different levels of liquid addition at 7.5% or 15% of the weight of the beans. And then we had this extra treatment there in the control column marked with 0, which was the beans directly after harvesting and crimping that were preserved as such. The composition of the faba beans was quite typical, 34% crude protein, 38% starch, and the moisture content, which is maybe the most relevant considering the current study, was quite low, 22% for crimping and ensiling. So that was our starting point, and then it indeed makes sense to add a little bit moisture there to ensure that we have some fermentation which promotes the preservation. And here in the bottom is also then the concentrations of the lysine and conlysine, the anti-nutrients that are present in faba beans. So they were here in this batch at a quite typical level of concentration. We preserved the beans in vacuum bags and let them ferment for 3 months before sampling for analysis. And then we move on to the results. So here it's all the 9 treatments next to each other. The first one shows the moisture content. So 21% for the seeds as such, and then at the first liquid addition level, the moisture content was about 26%, and then on the second one about 30%. And then the pH on the right-hand side. So the higher the moisture, the lower the pH, because there's more fermentation and more production of the fermentation acids. But there was a clear effect then between the additives. So the grass-wheat treatments resulted in lower pH than water addition or the formic acid addition. So that was actually maybe even greater effect than I was expecting. And of course, we are happy with the low pH. It helps the preservation. Here in these bars is the main fermentation products combined, and all the 9 treatments again there. And the red arrows show those treatments where there was hardly any fermentation. So in the control that didn't receive any liquid addition, it was so dry that there was no fermentation in practice, and also then the formic acid treatment almost totally also prevented the fermentation. And then the grass-wheat treatments showed higher production of fermentation end products and increase in moisture also. So this is very logical result. The amount of fermentation products provided by the yeast was very, very small, so it doesn't play a role in these results. So it did somehow promote the fermentation otherwise than just delivering the fermentation products within it. And then this was really nice. This graph here shows how much of the anti-nutritional factors, lysine and conlysine, is left after the fermentation compared to the original raw material. And on average, only 40% was left. So it's a nice result showing that this can indeed improve the nutritional quality of the beans for the monogastrics. And that treatment there in the middle that has the highest bars, that's the one with lower moisture addition and formic acid. So there the fermentation was restricted, and I think it's also a very logical result that when the fermentation is restricted, then also the degradation of the anti-nutritional factors is reduced. Here is some earlier results where we have also seen clear degradation of the anti-nutritional factors due to ensiling of faba beans. So I think this is quite well established effect. We did an in vitro ileal digestibility, which represents the digestibility in pigs, but we could not see any differences between the treatments and also not compared to the original raw material. So this was a little bit disappointing, and I'm not sure if it was a methodological issue or if that really was the case here, but we have some positive results about the digestibility from in vivo trials. So I still think there is scope also to increase the digestibility of the nutrients by this method. Here is the amino acid profile. This is, of course, very important for the monogastrics. So, there was very limited changes in the amino acid profile due to ensiling, and also quite little ammonia production. Ammonia is not useful for the monogastrics, but we do have degradation of protein during ensiling, but if it is to the level of amino acids or peptides, it can actually even be useful by improving the digestibility. But ammonia, of course, then is useless for the monogastrics. But then this graph shows something about the amino acid profile compared to soybean, and also compared to the needs of the monogastrics. So soybean is superior compared to faba bean in terms of the amino acid profile. And this is, of course, a particular problem for the organic livestock production, because the synthetic amino acids cannot be used to correct the amino acid profile regarding the missing amino acids. So to conclude, some pros and cons for this approach. So crimping and ensiling is an economic alternative to dry the seeds under humid conditions. And this, of course, I mean, here our focus in this project was the organic pigs and poultry, but this conclusion, of course, is valid also for other types of livestock production. And the reduced anti-nutritional factor concentration was demonstrated here again, which is, I think, quite nice thing to keep in mind. This grass we showed potential in to be combined with this crimping and ensiling process, and the challenges I think lie in many technical issues, like the timeliness to have the wheat available at the same time as the beans in the logistics, and how to do this, which technologies to use. So that is a little bit futuristic maybe at the moment, but let's see. Also, I think it's fair to expect that also the digestibility can be improved with crimping and ensiling for monogastrics, which can be a big benefit. And then in practice, how to also use these moist feeds for pigs and poultry needs probably adjustments and investments at farm level. And then compared to drying, of course, there are these potential hygienic risks in ensiling compared to drying. So issues that we are dealing with in general with the silage making, like aerobic stability and molding, and particularly with the grains then and seeds, the mycotoxins are one risk that can happen if the preservation is not successful. And of course, it's a fact that the amino acid concentration of the faba beans is not as good as, for example, in soybean protein. But I think that was all I had. So I thank you for your interest, and maybe we have some time for questions or comments. Thank you.
Thank you. Thank you for your presentation. I will ask for some question.
Yeah. Hi, I was seeing that methionine you mentioned that is the first limitation amino acids you means for the poultry. Yeah. If that case, The secondary was usually the lysine, that is threonine, and tryptophan was in fourth. Is there some changes in the Finland?
Now I must say that I'm not an expert in monogastric feed nutrition, so I think I will not maybe comment more in detail about those details. Sorry.
Okay, I would ask you, in Finland, faba bean is the most used leguminous for this reason, or maybe other legumes will have another amino acids composition, I think.
Mm-hmm. Yeah. The other alternative that we can grow in Finland is pea. So pea has quite low protein content, which is a limitation already as such. So faba bean is better in a way that the protein content is higher, but it would be pea or faba bean that we can produce here. No other legumes, seeds.
Okay, thank you. Still another question? Yeah. Still one.
Okay, Stanislav Vejduk, Mental University. I'd like to ask you, what about the pest? Because in Czech Republic, it was quite commonly cultivated legume, the faba bean, but there is a big attack of aphids and some beetles, and we need to use repeatedly insecticides, would make the cultivation of faba beans more complicated and also more costly. So that's no problem in Finland. How is it?
Yeah, I think maybe one reason why we don't have those problems is that it's not so commonly cultivated, so then the pests also don't thrive so well. But there was a big boom for faba bean cultivation maybe 5 years ago, but then it's been mostly the climatic conditions like drought in early summer and such things that the farmers have actually decreased the use of it. So it's still quite marginal, and currently pea is getting more popular as a legume seed in Finland.
Okay, so thank you for your presentation and also for your answers. Thank you.
Thank you.
And now we will continue with next presentation. You will come Zox from Brazil. No? Okay, so you can start. Thank you.
Before we start the presentation, hello again. So I was already yesterday here. Ivan Eisner, my name. I am from company Novanesis. I will show this presentation today. The trial was done by our colleagues in Brazil, but unfortunately they could not come and present it. So this is why they asked to do the presentation. So yeah, before we start, just an introduction. Yesterday, for example, we learned that ethanol produced by yeasts in the silage may indicate that the silage will not be palatable because high ethanol content in the silage that is produced by yeast can be correlated with alcoholic esters, and it is discussed that they may negatively affect palatability of the silage. So, yesterday evening we realized that ethanol produced by yeast is very good for humans. Yeah, if you drink it like wine or slivovica. So this morning some of us realized maybe it is good, but only in limiting amount, not that high like yesterday. We also learned that our Austrian colleagues struggling with butyric acid in grass silages. They want to have grass silages free of butyric acid, yeah, because butyric acid in grass silages is product of Clostridia that indicates also poor fermentation, yeah. But here I will show you now that butyric acid is not that bad, yeah, if it is not produced by Clostridia. So, why we did this trial? Yeah, silages, especially corn silage or grass silage at high dry matter content, the main problem is aerobic stability. Yeah, they're aerobically unstable. And we have only limited possibilities to improve aerobic stability. We can use heterolactic bacteria that produce acetic acid. And yeah, acetic acid also is discussed that it can also negatively affect palatability of the silage. And if we have high levels of acetic acid, the cows don't like this silage. Yeah? But butyric acid, for example, silages with high level of butyric acid, they are aerobically stable because butyric acid can also inhibit yeasts and prevent heating of the silage. Yeah. But unfortunately, if we have butyric acid in the silages, this is produced by Clostridia. But anyway, what we wanted to test? So we wanted to test effect of butyric acid and also acetic acid as an alternative on feed intake of the cows and also milk production and rumination, chewing activity, etc., etc., etc. Yeah. Also, butyric acid, for example, can also be converted to isopropanol finally, and this isopropanol theoretically can come to the milk. So, and we also wanted to test if it is the case, maybe in high amount, yes, but we don't want to have any alcohol, so especially isopropanol in the milk. We wanted to test also quality of the milk. So, what we did, although not me, so my colleagues in Brazil, I'm really happy that I was not there during mixing the diet because of butyric acid. We had control diet containing chopped Bermuda grass hay because we want to have any neutral forage without any fermentation, yeah, plus concentrate. And then we had the same control diet plus 10 gram per kilogram dry matter of butyric acid, and the same diet plus 16.5 gram per kilogram of acetic acid. Why we decided to use 16.5 gram? Because the study showed that till this amount, or till this concentration at TMR, we don't have any risk of negative effect on the total mixed diet intake. And we know that butyric acid is much more effective than acetic acid. If you want, theoretically, imaginally, to use it as, to have it in the silage, if it is not produced by Clostridia. So it is much more effective. It means we need less amount of butyric acid compared to acetic acid to get the same effect. So we mixed it with the diet, and then we fed the animals twice a day, and we milked the animals twice a day, and we analyzed dry matter intake, we analyzed eating time and intake rate, and we analyzed milk yield, composition, and also blood metabolites. So this is the design. So it was crossover design. We had 3 groups, and we had 3 periods, which means each group got all 3 diets one by one. So first 2 weeks was adaptation period, and the last 4 weeks was sampling and examination of the data. So, the results. So eating behavior, very interesting. So first of all, what we see, the eating time minutes per day was not different, but we see effect on rumination. It means, for example, the cows that got diet with butyric acid, they ruminated more. And ruminating is good. Ruminating, it means buffering of the rumen, improving the rumen health. Yeah? Ruminating was significantly higher. Chewing was tendency for longer chewing. Only maybe interesting also effect was fast meal duration. It means, yes, the cows that got, for example, diet with butyric acid or with acetic acid, the first meal was a little bit shorter. Why, we don't know. Maybe the smell was too strong. We don't know that. But finally, at the end of the day, it was no difference in the dry matter intake. Yeah? So here we have the dry matter intake, and we can see dry matter intake with butyric acid or with acetic acid as well was not significantly different to control. Yeah? Energy-corrected milk production for butyric acid and acetic acid was a little bit higher, but not significantly higher. But what was interesting that, for example, the protein content with butyric acid and with acetic acid was significantly higher compared to control. Maybe it is also an effect of better rumination. We have better conditions in the rumen. Yeah. So, yeah, beta-hydroxybutyrate acid concentration, as expected and as reported also in other trials, was a tendency to be a little bit higher, but in this case, sure, this is not the indicator for ketosis, for example. Yeah, this is because butyric acid is also absorbed in the rumen, and in this case, we have also beta-hydroxybutyric acid in the blood. So, but generally, interesting results. First of all, feed intake, not significantly different. Rumination is better. Protein content is higher. And milk alcohol test is also important, so we could not detect any milk sample with the alcohols in the milk. So, conclusion of the test. Yeah, not all fermentation acids reduce intake, so not all acids are bad. Even butyric acid is also not bad in this case. The dose matters. For example, for acetic acid, we know if it is below 17 grams per kilogram dry matter, it is no risk for any negative effects on the feed intake. And the moderate acid levels do not compromise performance, so we don't no loss in intake or milk yield. And it is opportunity. Butyric acid or acetic acid may increase milk protein. And sure, high butyric acid in silage now is still an indicator for poor fermentation by Clostridia. Yeah. Thank you.
Thank you for your presentation. I will have first question. Can you tell me how were measured feeding behavior parameters? It was personally or by some color or bolus? Do you know it?
No, there was special equipment on the cows.
Yeah.
So what measuring
some
everything.
color with.
Yes.
Yeah. Okay. Yeah. Thank you.
You see yesterday our butyric acid concentration in grass silage, and we have sometimes contents of more than 50 grams per kilogram dry matter. So my question, do you have knowledge about literature of limitation concerning dry matter intake of such high amounts of butyric acid to dairy cows?
No, we don't have any knowledge, and we don't have, so there were trials already with butyric acid, for example, infusion in the rumen, for example, without having any negative effects at all in the rumen and also in the behavior and feed intake. But as mentioned, if we have butyric acid in grass silage, yeah, now, yeah, because it is produced by Clostridia, higher is worse because we have also probably high ammonia content. We have also high concentration of biogenic amines. So, and in any case, if we speak about butyric acid in the silage nowadays, it is bad. So, but sometimes the cows like it and eat it. Even high levels of butyric acid in the silage, if they adapt to the silage, they will eat it. Yeah, we can speak about the negative effect on the health because there are also trials showing that if you have butyric acid in the silage, also we have higher counts of Clostridia perfringens that is not in the silage. Yeah, so in the silage we have another Clostridia. But we have higher levels of the counts of Clostridia perfringens in the gut layer of the cows. So it means we impact negatively the health of the cows anyway, yeah, because everything is at once. It's not butyric acid, it's maybe biogenic amines, maybe Clostridia that are already there, and the cow has to use immune system to kill first this Clostridia, and then we still have perfringens in the gut that can grow in that time. So a lot of factors that we have hypotheses, but don't know exactly. Yeah. There is also recommendations, for example, I think no more than 50 gram butyric acid per cow per day. It was American recommendation. If we have silages, then if we calculate the diet, the full diet, we have to calculate not to exceed the total amount of butyric acid 50 gram per cow per day. So this is official recommendation from America, yeah, for example. Yeah.
Thank you.
Yeah.
Thank you, presentation. Maybe I don't hear very well, but you added butyric acid as separate butyric acid relation, yes?
Yes, yes.
But this butyric acid came with silage. It can be different. Because when producing butyric acid in silage, some another factors can influence.
Yeah, sure, yeah. But let's assume we find any bacteria that can produce butyric acid in the silage without negatively affecting the protein quality, whatever, and we get the aerobically stable silage with a little bit butyric acid, and butyric acid is good, we're lentil ready, we improve the rumination, it just also has prebiotic effect, yeah? We can feed it even for the small calves to improve the rumen development.
What I would like to say, butyric acid, it's not bad for dairy cows, like acetic acid.
Yes,
but butyric acid in silage showing it's a little different. If you added the poor butyric acid generation, it's different than this go with silage. What is
correct.
Quantity of butyric acid.
This is not the butyric acid that is bad for cows in this case. Yeah.
Thank you.
Yes?
Butyric acid is the indicator of degradation of crude protein, yes?
Yes, true.
But Clostridia, they produce also from amino acids, biogenic amines.
Yes, correct.
And that is poison.
Exactly.
Yes, because butyric acid is not. And my question is, if you tested how much biogenic amines and which you tested in the silage?
Again, can you repeat it, please? Yes.
Which, if you tested or analysis, except the butyric acid, other biogenic amines?
Oh, yeah, there are a lot of studies also showing the increase of biogenic amines if butyric acid content is increased because it is natural degradation process from Clostridia that use protein as a energy source, yeah, which means they degrade amino acids to ammoniac and biogenic amines, yeah, and the correlation is there, it is positive correlation. Also, the smell of the silage is not only butyric acid, sometimes it smells like shit because of biogenic amines, yeah, putrescine, cadaverine, etc., yeah.
Okay, it's all. Thank you for answers. Next presentation by Khan will not be because they cannot present it. So I ask Mr. Kumprecht, come here and present your presentation, which called the effect of feeding poor quality silage on rumen fermentation processes, metabolic profile and health status of dairy cows. Thank you, and you can start.
Good afternoon, ladies and gentlemen. My name is David Kumprecht, and me with my colleagues, we prepared this study on evaluating the effects of feeding poor quality maize silage and affected by secondary aerobic fermentation. It had its effects on rumen, blood metabolic profile, and the health status of dairy cows. The study was conducted on a commercial dairy farm which was experiencing a sudden decline in performance. So, why is good quality silage important? Silage is the main component of the total mixed ration, and therefore it has major influence on nutrient intake and rumen function. Good quality silage supports stable fermentation, high milk production, fertility, and overall health. However, during feed-out, especially in the summer months, oxygen penetration may trigger secondary aerobic fermentation, leading to deterioration of the feed. So, what does happen during the secondary fermentation? As the oxygen enters the feed, the yeasts multiply and they start metabolizing the lactic acid, and the temperature starts rising as well as the pH of the maize silage. Then the higher pH and temperature supports the growth of molds and bacteria, and mycotoxins and biogenic amines start appearing. And it also leads to deterioration of the feed quality, the dry matter losses, and losses of carbohydrates. So this is a typical picture from a farm from summer months, for example, when you have the silage bunker. If on the edges it is not isolated well, you can find silage moldy as this one. The impact of rumen is when you are feeding spoiled silage. It reduces the supply of fermentable carbohydrates and decreases protein digestibility. At the same time, mycotoxins negatively affect rumen microorganisms and protozoa. These changes compromise rumen fermentation efficiency, and reduce the production of volatile fatty acids. The consequences for cows are that the poor fermentation leads to lower feed intake and metabolic disturbances. And then it reduces milk production. In addition, exposure to mycotoxins and biogenic amines contribute to increase somatic cell counts, lameness, reproductive disorders, and overall deterioration of animal health. The objective of our study was to evaluate the effect of feeding spoiled maize silage on rumen fermentation processes, metabolic profile, and overall health status of dairy cows. The study was conducted on a dairy farm with approximately 500 cows in Central Moravia. we are collecting urine fluid and blood samples for laboratory analysis. In urine fluid, we evaluated volatile fatty acids, protozoa, and ammonia, while blood samples were analyzed biochemically. The silage itself was examined for the presence of mycotoxins. We went to the farm because there was sharp decline in milk production by 3.5 liters per day, together with somatic cell count almost doubling. Farmers also observed a reduced feed intake, and the laboratory analysis confirmed elevated mycotoxins just as deoxynivalenol, T2 toxin, and zearalenone. Well, on the sides of the silage bunker, there was some discarded silage, and there were mushrooms growing, just like in this picture. So it also gave us an idea on what's going on. In the rumen fluid, the pH remained in the physiological range. However, the volatile fatty acids concentration was reduced. The physiological should be at least 80 millimole per liter. Also, the protozoa were reduced. However, the proportions of individual volatile fatty acids weren't changed, just like ammonia also wasn't changed. And for blood biochemistry, it suggested liver involvement and muscle catabolism, reflected by elevated aspartate aminotransferases and creatine kinases. Also, we observed decreased concentrations of calcium, zinc, and vitamin A, indicating mineral malabsorption and disturbed vitamin metabolism. So, clinical consequences. The laboratory findings help explain the clinical problems observed on the farm. Impaired rumen fermentation reduced nutrient availability, while mycotoxins and biogenic amines contributed to systemic inflammation and metabolic dysfunction. These mechanisms can lead to several important clinical consequences, including lameness, weight loss, reduced milk production, and increased somatic cell counts. For lameness, mycotoxins and biogenic amines may damage the ruminal epithelium and increased intestinal permeability. That allows endotoxins and biogenic amines to enter the blood, and it results in systemic inflammation and may affect hoof microcirculation, which can damage the laminar corium. There's similar mechanism in mastitis. The mycotoxins and biogenic amines also disturb immune functions and cause systemic inflammation. It leads to leukocytes migration to tissues and to mammary gland, and it contributes to elevate somatic cell count. And the barrier in the udder also may get damaged, and it may result into clinical mastitis. The uterus is sensitive mainly in the postpartum period. Mycotoxins may impair immune response and delay uterine involution. At the same time, systemic inflammation reduces the ability to eliminate bacterial contamination after calving. These factors increase the risks of uterine infections and then endometritis. The reduced feed intake and poor rumen fermentation decrease energy availability. Cows compensate by mobilizing body fat reserves, which leads to elevated non-esterified fatty acids and, of course, negative energy balance. The fat mobilization negatively affects liver function and increases the risks of metabolic disorders, just as ketosis and fatty liver syndrome. Also, the reproductive performance is closely linked to nutritional and metabolic status. The negative energy balance, systemic inflammation, and mycotoxins, especially zearalenone in this case, they negatively affect ovarial activity. So oocyte quality, embryo survival, and may lead also to esters, lower esters manifestation. As a result, the conception rates decline, ester cycles become less regular, and the calving interval may be prolonged. Milk production depends on adequate nutrient intake and efficient rumen fermentation. Spoiled silage reduces milk, feed intake and decreases the production of volatile fatty acids, as I said. They are the main energy source for dairy cows. In addition, inflammation redirects nutrients away from milk towards the immune system. Together, these factors lead to reduced milk yield and poor production performance. So, to conclude, aerobically spoiled silage negatively affected rumen fermentation, metabolic status, and overall cow health. Reduced volatile fatty acids production and protozoal counts were accompanied by metabolic disturbances. Liver damage, muscle catabolism, and mineral malabsorption were observed. These changes were associated with reduced milk production and increased somatic cell count, highlighting the importance of maintaining good silage quality throughout the feed-out period. Thank you for your attention.
Thank you. I have again a first question. You told that a farm have 500 cows. How many cows was used for sampling?
I think it was 22.
22?
Yeah, 22 cows.
And they were taken about milk decreasing or about somatic. What was the main reason that this cows it will be? Or combination?
Docent Ilak knows that. I'm not sure. I can't remember that.
Okay.
It's been a while.
So, fine. Have you any questions?
Can you pinpoint the reason why the silage was so bad? Was it like a mistake into the harvest point? Was it not well packed, or was it not covered well?
Well,
combination maybe.
it was, I think it was August It was the middle of the summer, and also I felt like it wasn't covered properly. Yeah, it was in the silage bunker, and yeah, you could see like on the edges the mold. I'd say it wasn't covered properly.
One comment on those pretty mushrooms you showed us. We have a case a few years ago of in Germany, also in Ireland. So this could be Schizophyllum communae. It's a tip. We have some expertise of Bavarian colleagues. They they have identified this species, so I could share those information with you.
Thank you.
Thank you. If some question? No. Thank you very much for your answers.
Thank you.
I think that it is very important to show to farmers that this happens when is something like this wrong. Yeah. So, and now will be the last presentation. It is from Slovakia, Bobček, yeah, Mr. Bobček, and yeah. So. You can start.
Yes, everything working. Super. Thank you very much, ladies and gentlemen. Thank you to stay and listening last presentation. This will be a little bit different topics. Topics about soil. Soil, it is like main basic production resource. If you from the quality of soil dependent which kind of crop you will have. And therefore we did trial in Slovakia with Slovak University, and we reclamation a very degraded soil land after the mining. This is gravel, and this was big mining gravel, and they destroy absolutely this soil and land and take almost 0.8 meter, almost 1 meter, to the top soil. And we did trial if it's possible to recover by microorganisms. Main important substance in the soil is humus. Humus is very important to be there in the soil. If you have enough humus, you can do good yield, good quality of crop and forage. Humus, it's clay-humic complex, which is also a refrigerator for the elements. It means they keep like storage elements for the plants and keep the water. It can absorb water very fast and also keep water in the very dry period. And it's also structure. Structure is very important for the aeration of the oxygen in the humus. It is a little bit different topic like silage. I can say like opposite. I will explain why. Background, why we found courage to initiate this trial. Because this soil was absolutely dead. It's only rocks. And we get courage thanks to farmer Marcel Mézy from the French. And he is inventor of the technology create microorganisms by composting bacteria and fungi. It is a content of spontaneous composting microorganisms, technology Marcel Mézy. And he also start its revolution in agriculture, microbiology. We have after Second War mechanical revolution. Later we have chemical revolution. We put fertilizer. We have pretty high yield thanks to fertilizer, but now it's come back, look to the soil, and we start to do revolution of microbiology. Why this technology? this technology is very important because it's very variable microorganisms, and we know, and you know, because you're working in the silage business, that is very important is balance of microorganisms in the natural, in the intestinal tract, in the silage, and this balance is very, very important. And it's most organisms is beneficial and have proper function in the gut, in the silage, in the soil, digestion protective barrier, but always exist and there, be there also pathogenic microorganisms. And they want to also survive. Yes, they took nutrients and they want to survive. Therefore, this balance is very important. If we can do balance also on the soil. And if we is more pathogen, we have disease and plants disease and lots of other. This is Marcel Mezi. He is inventor of this technology, and he developed exact technology how to create microorganisms by composting dozen of plant and tree species. It is very long composting period. He makes these species and he create population of any kind of, more kind of organisms. Which kind? This is very important for microbial biodiversity. Diversity is more important in the soil, like if you have just small scale of the bacteria. But diversity is very important for the soil because have more purpose agronomic, you see, agronomic function, and it's more adaptive. We can say it is new microbiology terminus. It is functional redundance. Functional redundance, it is very huge amount of strains of bacteria, microorganisms, which make a good balance and develop complex on the environment. It is make a new ecosystem on the soil. French Institute, National French Institute, prove that this product have 28,000 strain of detected different kind of microorganisms. It is not only bacteria, it is also fungi. It is fungi, rhizospheric and mycorrhiza, and there is a minimum 50% from the strain is fungi, because soil need fungi. And it was detected by genomic, transcriptomic genomic system technology. Which kind of the bacteria microorganisms is there? There is microorganisms which trap nitrogen from atmosphere. It is over 120-30 strains include. Recirculation nitrogen in the soil and from the animals is 216 strain. And also microorganisms over 2,500 strains which can bring available phosphorus from the soil. It means farmers don't need anymore use to fossil phosphor for the feeding plants. Therefore, we can say, if we feeding soil, we don't need to feed plants. If it's soil enough and life, it's enough for the feeding these plants. What is difference, Mr. Mezi, Dr. Mezi, and laboratory colonization of bacteria? This is difference because it's making in the compost. He create lots of population colony of microorganisms. He not create or doubling, tripling, 1, 2 strains of bacteria. He don't create, not produce this bacteria in the bioreactor. It is also good, you know, because you use for silaging, producing bacteria, maybe 1, 2, 3, 4 strains, and keep the same strain, and helping you to control the silage fermentation. But this product is opposite. They create in the natural, in compost. And there are 4 families, main families or population of microorganisms. Autotrophic, taking carbon and mainly nitrogen from atmosphere. Therefore, is aerobic. They cannot be plugged into the soil, must be put on the top. They like oxygen, sun, and they need also moisture, of course, water. Decomposition bacteria, which is destroy lignin, which you have on the soil. If you plug in this and some forage, humic organisms, which is create humus, which is big storage of the minerals, and rhizospheric microorganisms, which is promote to helping to create more and more roots system. And this is game. After this application started in the soil, the game. Game is that plants want from the soil minerals. Minerals, they want plants, but humus, bacteria, they need sugar. It means plants have to produce sugar thanks to photosynthesis, send through roots to humus sugar, and this sugar make more humus, and humus gives them back to minerals. Therefore, plant is not anymore lazy. If you apply fertilizer, they are very lazy. You have very small roots, very sensitive. If you start this game, that is creating a very big root system, after this, plants is healthy, is logical. And there are two products putting on the soil. It is like soil, pellets, or putting to do compost, manure, slurry, or digestate. And this is the same contents of the bacteria, of microorganisms. We know from the soil profile, we start organizing also in Czech Republic, also this year, and we know that we create humus deeper and deeper. After 2, 4, 6, 8 years, 1.8 meters, comparing to control. It means if we create humus deeper and deeper, the humus layer keep the water for the forage, for the plants, and also giving them enough minerals. And then now is this trial. We did trial with Slovak University, and it was close to Levice. They took top of soil 0.8 meter, took out and mining gravel. Mining gravel for the concrete, it's building company. And they almost half hectare they took, but if they want to mining more, here is the river Hron, they need to recover this soil. After, ministry can give them other land to be mining this gravel. And therefore, they asking me if we can recover this soil. And looks how it looks, this topsoil took off, and this is absolutely rocks, very dead soil. It's not possible to put to some hectares very black quality soil. Almost 0.8 meter is not possible. Therefore, they have, if they cleaning this gravel, they have very clay sand. This is waste product from the gravel mining. It is sludge. And they put almost to top this sludge, this is waste product from the washing of this gravel. And after we put there also bacteriolide with compost. Compost we treating with bacteriolide, with bacteria, and put on the top of soil. Not put in, because it's aerobic microorganisms. How we create this compost? This compost create cross to nitra, which they collect waste product from the fruit, vegetable industry, and mixing with hay, spoil hay or straw. This was hay. And after 3 months, they go off almost to half, didn't lose weight, but was composting after 3 months. And we didn't find any bananas, citron, grapefruit, nothing. It was compost very well. We cannot see it there. It's coming, inspector, they checking, oh, where is, this banana and fruits like citron, grapefruit, we will have there next 2 years. No, bacteriolide helping to compost very fast. and don't need to aerate. Its aeration is very important for composting, but not with bacteriolith. Usually, for the silage is dangerous if we use overheating. Here is opposite. We need to overheating soon as possible. It means if we start to composting and we increase temperature up to 50-55 degrees very fast, and temperature will go down, compost is done. Sometimes people which not use for compost bacteria, like from Mr. Mezzi, they heating sometimes half year. Poultry, chicken manure, 1 year. Sometimes can be fire, burning. Therefore, I be checking this temperature, we going up and after go down. We don't need any more aerate. Usually big compost company, they need to purchase this machine and have to minimum 2-3 times per week do it aeration to prevent the overheating. And this is the results. This is control fulvisol. It's a regular soil where they growing forage. And here is anthrosem, which is destroy soil. And there is, after 23 apply, start the trial, and 24 analyze. We of course continue this trial because it still is not okay. And we can see that we increase pretty significantly carbon in this dead soil. It is sand clay. And also we improve pH. Yes, close to, because humus is close to 7, therefore it's better pH like fumizol. And from these results, we can say that it's this really bring the life and humus carbon to do this dead soil. And after 1 year, we can see almost 1.5 meter corn. Its institution said, oh, this dead soil you will have minimum 10-20 years nothing, no yield. And we have after first year this kind of the corn, very nice from this. It was almost 5 tons. They comparing Professor Kapolakova with average, but this was very dry year. You remember that if it's very dry year, no raining, you have not 10 tons of corn, but it's much. Therefore, they comparing these years. And also we did Czech Republic trial after 3 application. Starý Hrozenko, Vyškovec, it is very poor soil in the old Czechoslovakia. It is 600 meters from the sea, and this is a small farmer, he is retirement, and he said it's institution and they know is never will grow alfalfa. And after I explained him, oh, it's no problem growing alfalfa in your field. Yes, it's not possible, never growing. And he put bacteriolith with manure and bacteriosol. He changed how much manure he have. And he on his field, you can see how much forage. And his neighbor's field, almost 3 times less forage. And his alfalfa in the garden, he have 5 cut in end of September during year. Not 1 cut, 2 cut, but 5 cuts. And very nice, during 1 month and 5 days, was again growing to up to knees. And this, therefore, we know this conclusion that concentrated a bacteriolith by technology Marcel Mezzi, farmer can activate manure or compost into the active medium capable of fertilizing even waste sludge from gravel, which can be used in the subsoil layer and also recultivation degradable land. It means if you have any kind of quality of soil, if you have very, very dry period, my customers have minimum 100 to 150% more forage now in Slovakia when it's almost 2 weeks didn't raining, like neighbors farmers. It means also this soil keeping for the plants, keeping water. And also we did in Hungary, 2018 soil profile. They can see after 8 years, almost 1.8 meter humus. Sylvia is not here. Sylvia knows this story. She was there, and also my customers immediately purchased this bacteriosolid, and they would like see what happened. And after 3 years, we opened the soil, and they create from 30 centimeters, 35, 1.2 meters deep soil humus layer, and they know that they really creating. And they have comparing 220 holes worm per meter square with treating with bacteriolid 820, almost 4-5 times more of hole after the whole worm holes. Yes, because these worms, they are they doing replace your plugging. You don't need any more plugging because these worms aerate your soil to deep up to 1.5 meter. Yes, and we can decrease manure almost minimum to half. Yes, this is it's my presentation, and if you have some question, I will be happy to answer.
So thank you. Have you a question? So I would ask,
yes.
Your recommendation is that one application is enough, or a few years?
Yes. One application is enough if you can stop using pKa, like phosphor, potassium, carbon, not nitrogen. This mushroom little bit took nitrogen. Yeah. You need to put the plants nitrogen. But if you want to see really create humus up to half and 1 meter deep, it's minimum 3 years.
Okay.
Therefore, we open field and doing soil profile after 3-4 application.
Okay. Thank you. So thank you for your answer and your presentation. And yeah, you have, there is one question.
Dusan, there is some period where is the best to start on application, and it's 1 year or twice a year. And are there any other better recommendation from your side?
Regarding producer, is best application is spring or summer or autumn, because these bacteria and fungi, mycorrhiza, they need temperature minimum 6-8 and up. Don't apply it if it's freezing, because they will not wake up. And they need rain or minimum spring water, rosa. How to translate? Ranna rosa. Echo? Yeah, yes. A little bit wet, morning wet, yes. And today I have some orders, because from the High Tatras they asking me for the bacteriosol, and they said, but now is not anymore spring. Yes, but this period is moved because we have in April frozen. It means now is best period to apply because it's raining, and also it's morning this moisture. And this is enough for them. And they like sun, oxygen, temperature up to 8, and they like, yes, moisture. And also it's very dangerous, you cannot after application manure or bacteriosol minimum 14 days spraying fungicide. Because fungicide you can kill this mycorrhiza and you will have no effect. It's mentioned on the leaflets, and also pesticide like herbicide, fungicide, insecticide. After 14 days you can. That's it. Yes, good question. Cost per hectare is variable because it's 2 products but it's same contents. First invention was bacteriolid for the manure. Mr. Mezi, he is farmer which have animals. He is from Toulouse, he have Aubrac, he have sheep. And bacteriolid is applied between 2 animals. And if you apply to manure between 2 animals, the cost is about 4.2, 4.4 euro, depending how much packaging you take per hectare. No, 4.4 is kilo, and 30 kg is per, it's 130 euro per hectare. Bacteriosol was invented 8 years later because fruits farmers, they want also this bacteria and fungi. And he created new products, bacteriosol, which is pellets, and you can put pellets on the top of soil, and this is from cacao shell nut, and this cacao shell nut feeding this mushroom, and they create this mycelium in the soil, and this is cost over 220 euro per hectare. It's more expensive, and much cheaper it's animal farmer. And also in Slovakia, they are more buying farmer which have manure, slurry, or digestate. Also biogas station they like if they have soil, because not anymore destroy soil by digestate. Yes.
Okay, thank you. So it was the last presentation, and thank you for your attention and also for questions. And I think finishing of this conference will have Sonia.
Okay. Thank you for your attention. Thank you for your presentation, posters or here. Yeah. So there is some invitation for the next event in Germany. So if you want, put it into your calendar. And I thanks our sponsors. Our sponsors for EcoSeal from a Vola company. Okay. Oh. For Vola company, thank you VVS, it's a Czech company. Thanks Dr. Pieper, Patient Egg, LG, Biofarm, Torsil, and our cyber partners, Salinity, Bayer, Christian Hansen Novonensis, Valibiotics, and Strom Praha, partner John Deere, Agritechnica, Agratio, and Product Feed. Thank you all of them. Because we find a place and it will be, I'm sorry, I have no words about it. Thank you because we can meet here. I'm really glad that there was 130 participants. Maybe it's not visible here in the aula, but the foyer was full. And I hope that in 3 or 4 years we can see again. And it will be much more participants how it was before COVID time. So thank you. Have a nice flight to your home, and we are looking forward to see you again. Yeah, for those who are here for excursion, this foyer will be closed tomorrow. We will meet in front of aula at 8:30 in the morning. Bye.